Okay, I'll just introduce Daniel here, Holbleck. He's from the University of Calgary. He's a professor there in the physics department for quantum. We've been working with Daniel's department for quite a long time. Since 2015, we've supplied them just with some fiber optic cable for them to do their entanglement experiments, and we're still working with them for providing them that infrastructure for them to do their experiments. But Daniel's here today to do his presentation, so I'll hand it over to you.
All right, thank you very much. I think, can everybody hear me in here? Or is it for the online? I see, yeah, that makes sense. All right, so thanks again for the invitation to present here. And as Dave mentioned, we've had a long collaboration with the city of Calgary and still have it. And I think, you know, the Calgary has been visionary in many ways of how they build out their infrastructure and make it available to us. So what I'll be giving today is, you know, quantum communication in Calgary. So it's a mix of a couple of different experiments over the years. So I had to dig up some older talks and some newer talks and blend it all together, because what I really want to show is a little bit about what kind of things we've been doing in Calgary, what's the history of quantum communication research in Calgary, and you know, highlight also the parts where the city has been involved. So let's get started. Quantum in Calgary has been around for a while. So the Institute for Quantum Science and Technology was founded with a slightly different name in early 2000s. And right now we have a lot of research groups, and we're expanding greatly with roughly over the next couple of years here, doubling the number of faculty members over different departments from math, chemistry, engineering, physics, and computer science that work in quantum, in the field of quantum technology and quantum science. And we also have some a foundational center called Quantum Horizons Alberta, which is starting up, where we'll be doing very foundational research in quantum. We have Quantum City presenting later on today, so I won't talk too much about that, but lots of initiatives from a clean room to events to a professional master sponsored by by Quantum City. I myself am a prof, as Dave said, at the physics department at the University of Calgary, and I called my lab the Quantum Cloud Lab. Because we're building a quantum cloud. If you want to look us up on social media, there's a couple of things. And this is a photo that I myself took. So when I go abroad, I always show people how beautiful Alberta is, and hopefully that will attract some people to here too. Here's who we are. This is our stint at being structural engineers. We're trying to see when this bridge will break. So far, so good. So we'll keep expanding. Now I know that you've had some presentations on what is quantum, so I won't go too much into detail about that. So thank you, Kubo, for doing that for me. I will, you know, just to give as everybody on the same page, say that, well, what is quantum mechanics? It's the theory of really tiny stuff, generally speaking. Of course, there's no, in principle, limit to how big quantum systems can be. Hence, Schrödinger's cat is the famous sort of thought experiment, but it's not realistic to have that large systems acting quantum mechanically. So generally, it's all the small things. What is quantum information then? Well, quantum information is taking the principles of classical information theory, where we have zeros and ones stored or communicated or dealt with for processing on these classical devices there. Hint, some of them actually use quantum mechanics as well, of how they work, but the information is stored classically. And then we say, well, let's see if we can put that over into some sort of a quantum system. And when we do that, we enter a realm where bits become qubits, and we have these states where we have zeros and ones, just like classical bits, but we also have these wonky things here that are superpositions, where we have 0 plus 1s or 0 minus 1s, and they're all different. And we can encode them into, let's say, different energy levels of atoms, or we could choose polarization states of light, and we can say that as long as those two are orthogonal, they can serve as zeros and ones. So if you measure 0, it's a 0, and you measure 1, you know it's a 1, right? But the superpositions is what really makes it unique. And so what is a quantum communications network? Because that's what I'll be talking about. So very broadly, we can say that it's some sort of a system that facilitates the distribution of quantum states over a distance. So one thing is to have these quantum states in one place. Another thing is to share them with your friends or enemies or whoever, and doing that over some amount of distance. And that's sort of the essence of the research that we do, is to create these states, to transport them, and then to measure them. So, you know, what is a quantum network? Could it be photons that are emitted from a single atom decaying over, and then moved over, let's say, a free space channel or fiber? Yeah, that would work as a quantum network. We can encode quantum information into these single photons. But sort of a laser death ray, too many photons, not quantum, very classical, okay? So we have to be at the very weak, very dim light level. Put an atom inside a box and ship it, you know, if that box also contains a cryostat or something like else, you know, well, it could be a quantum network. You could build a quantum network where packages are just sent between different places in the world, as long as you can keep your this atom, very, very isolated and nicely. Whatever this is, not a quantum network, you know, very classical. Although interesting sideline here is that birds actually use quantum mechanics to navigate. So they have magnetic sensors in their head somewhere that sense the magnetic field. So maybe a little bit of quantum still in there, but not communication, sensing. Okay, so of all the things we talked about, the most practical still for transmitting quantum information is going to be light. And why is that? Light, as in photons, when we go to the single, very, very dim light level, is that, you know, as we know, photons, light is really fast. It doesn't actually interact a lot with its surrounding. It's very easy to isolate. And then they have a lot of things that we can use to encode the zeros and ones. We call those degrees of freedom. The polarization will be one of them. So polarization, as I said here, we have the horizontal and vertical. And if we create superpositions of a horizontal and vertical, depending on the sign between those superpositions, we can have diagonal or an anti-diagonal polarization. So depending on how we make those superpositions, we can encode, or how we rotate the polarization, we can easily encode different polarization states. And we also actually, right over there, I think there's some polarization elements, some rotators, so we can, you know, manipulate polarization. Very easy way to encode quantum information, very easy to understand, and the one that's also was used in the beginning for a lot of quantum information work. We actually prefer to work with something else, which are called time bins, where you encode quantum bits into an early or late arrival time, and then we create superpositions of early and late. Sounds weird that you can do that, but basically when you don't know something about a photon, it's as if it's in a superposition. So if you've split a single photon in two and then merged them into the same path, then you can not know whether it arrives early or late. So you can create these things as well. There's different ways to encode quantum information, and these ones tend to be more practical for us. Okay, so how do we then transport these photons that have encoded our quantum information? Well, we can choose one of two ways. We can go, just generally speaking, we can go through an optical fiber, and of course this is very convenient and practical, and there is fiber networks all around the world, including here in the city of Calgary. We could also choose to go over a free space, just shine a laser beam, dim it very much, which obviously has some problems because you can't have obstacles. Most people believe that there is a curvature of the Earth. give or take a minor small percentage. And so there's a limit to how far you can go in a straight line as well. We'll get back to that later on to see where this free space communication actually comes into play. But for the moment, we're going to talk about the fiber optic channels. And the one thing to note is that even though fiber optics is very good, they do actually lose some of the light. So there is a bit of scattering of light. It's down to sort of 0.142 dB per kilometer, so it's very small, but it is there. And this is at a specific wavelength as well. That is the optimal one for telecommunications. So how we choose to transmit our light is going to determine where we want to go. In essence, how far we want to go. So before I dive into that, let me just briefly touch upon the use cases of quantum communication networks. I think some of it was touched upon. We talked about, quantum key distribution, which is a way to exchange cryptographic keys that does not rely on mathematical problems, or the hardness of mathematical problems. So the kind of cryptography that you're able to implement this way is what we call information theoretically secure, as opposed to being computationally secure. And the problem with the current cryptographic systems is that the protocols offered by quantum computers would actually be able to break them if the quantum computers are large enough. Of course, quantum computers are also being built, and you may have only so many quantum bits in a single, or quantum processors on a single system, and you might want to connect them to have a larger system, and in that case you need a network. And we all can appreciate how the internet enhances our experience with classical computers. So, and I don't think that people back in 20, 30 years ago could quite have imagined what the internet has become today. And I think similar to that, we can come up with some ideas here, but I don't think we can quite imagine what a quantum internet would do for quantum computers. But a lot of it circles around security. There are certain things you can do privately, securely, in terms of connecting quantum computers over a quantum internet or a quantum network that are just different than anything you can do classically as well. And then we talked about quantum metrology or quantum sensing more broadly, again, where somehow doing measurements that are distributed over a large distance enables you to increase the sensitivity of those measurements. And sort of, if we could illustrate quantum networks with one sort of like, with one picture, it could be maybe something like this. Let's start with the fact that those who are not familiar with Pokemon, this is a turtle. So a turtle is rather slow, right? So quantum networks are not particularly fast, but it has a shell. So it's pretty secure, like more secure than other networks. And then it's a Pokemon. So you do something to it, you call it, and it has some very special magical properties. So that's how you can envision a quantum network being. Slow, secure, and a secret sauce. Okay, so this brings me to the highlights of quantum communication in Calgary. And here's where I'll touch upon some of these applications and some of the methods used to transmit, but in this context of the quantum communication as it evolved here in Calgary. Okay, let me get a sip here. So, quantum communications came to Calgary, at least the experimental part of it, roughly in 2006. So, in that point, the Quantum Communications and Cryptography Lab was founded by Professor Wolfgang Tittel, who came from Geneva, where they had a lot of quantum communications research going on. In fact, some of the first QKD experiments were done from Geneva to some neighboring cantons or cities using QKD as a first time. So the group here was started around 2006, and I think this picture is from 2008 or 2009, which is just before I came to Calgary. A couple of important experiments and demonstrations were done at that point. So the first, task that's really important is to move these types of experiments out of the lab and into the real world. And in the real world, you think it's just the same as the lab, but there's a whole bunch of challenges that you're faced with in terms of stability and in terms of actually communicating and linking up all your equipment over a long distance. So the first effort, or some of the first efforts, were towards getting a real-world link. In this case, in the beginning, it was a link between the University of Calgary and SAIT, so it was a joint research project between those two institutions. And the first thing they did was to implement this BB84 protocol. It's named after Bennett and Brassard, and Brassard is from Montreal, so one of the first quantum communications or quantum cryptography protocol that was proposed, and the one that's sort of the hallmark of most quantum communication. So I don't remember, was this introduced earlier today, BB84? No, we were more high level. So I'm not going to talk too much about it either, because it take a long time. So let me see if I can distill quantum cryptography protocol in like a minute or so. We are familiar with the bases, right? So we have these different bases of photons, and they can be encoding zeros and ones, and depending on the basis, we can say that the vertical and horizontal encode zeros and one, or the diagonal and anti-diagonal encode zeros and ones. And the main thing to know about quantum mechanics, which I think was covered, is that it's probabilistic. So if you have a single photon, it has to decide whether it is a 0 and 1 when you measure it in some way. And so where Alice, who is sort of the archetypical sender of quantum information, encodes these four different states, Bob just chooses a basis to measure in. And if he measures in a correct basis, so let's say it's the horizontal vertical one, then he will know exactly get exactly the right outcome if Alice also prepares in that basis. And same way in the diagonal anti-diagonal, if Bob chooses the correct basis, the same one as Alice used to prepare her bits, he will measure 0, 1 correctly. If they choose different bases, Bob has a random outcome. He can measure anything because it's completely random which outcome he measures in that case, because it's an equal superposition in that case. So what that means is that if they choose these bases and the preparation bases and measurement bases randomly, half of the time they'll choose the wrong one. And those or do not match up their choices, and in that case, we just discard them. In the cases where they choose the same basis, Bob should measure exactly the correct bits that Alice sent. But the problem is then for an eavesdropper who wants to intercept this key, that they also have to choose a measurement basis. And when the eavesdropper chooses the same basis that Alice and Bob chose, then they can get away with stealing the bit. But if they, as they will half of the time, choose the wrong basis, well, in that case, they get an outcome, but when they try to recreate that photon and sending it onwards, they recreate the photon in the wrong basis, and now Bob's measurements are random. And if they're random, that means that half of the time he gets out the wrong measurement results. So if you kept track of the probability, was half of the time, so 25% of the time, Bob will be detecting the wrong bit values. And if they compare that afterward, a subset of them, they can see that somebody is causing excess errors on their link, and that is how they can verify, well, they can detect if somebody is trying to steal the key, and if so, they just don't use that key to transmit a message. And if it all clears, well, they go ahead, use that key, they've verified that they now have a shared secure bit string, and that's what you need for encryption. All right, a little bit more than a minute, but close. So this system was then implemented through a fiber optic link between Calgary and SAIT in 2009. Maybe 2008 was when it was done, but then it was published in 2009. And here's an example of the system. We see some transmitter box here where they prepare the states. That's this part here, and then here they have a receiver state, and these 4 big chunky boxes here, those are the detectors that were used at that time. And was published here in 2009. And here is an excerpt from the paper as one of the figures. Calgarians say it, so literally put Calgary on the map. And excuse me, a lot of the studies were about looking at how the state fluctuates depending on the outside temperature. And it's always nice to see that you're in Calgary when you're plotting like -16 and stuff like that, right? We always try to measure on the coldest days of the year just to show off how tough we are. The problem with this protocol, though, is that the detectors, they're vulnerable to attacks. So people have found out that even though the protocol in principle is secure, you can try to find weakness in how the experiment is realized. For example, you're assuming the detectors measure single photons and click in a certain way, but then people like this come around. This is Vadim Makarov. He used to be at IQC, right? And he has the looks and the logo and everything. Now he's elsewhere, but he was behind several of these attacks on the QKD systems. And if you look sort of at the list here, you see that a lot of them are on the detector, right? So the detector is clearly the weakest part of the system. So is there a way to implement a quantum key distribution protocol that is not that's resilient to these attacks on detectors? And it turns out there is. And it's called, very imaginatively, measurement device independent QKD. So, warning, a few equations up ahead. Don't worry. You don't need to. I'll try to not talk to the equations, but for all the nerds, you can say that you went to a talk and you saw lots of equations. So here we are. What is measurement device independent QKD? Well, we have Alice and Bob. They're the usual culprits that want to communicate some secret. And again, they choose to encode their information in different bases. We have the plus basis, horizontal, vertical, or this cross basis where it's actually diagonal polarizations. And they then enlist the help of Charlie. And what Charlie does is that he measures on one of these states here that's listed up there. So we have 4 states in total with the plus minus is taken into account. And those are the Bell states. So they're what we call maximally entangled states. And what you can see, the way to understand this notation, and we'll focus on the psi state here. We love Greek letters, by the way, So what this means that if one of the people measures an H, the other one has a vertical polarization. And if the other person measures a vertical polarization, the other one has a horizontal polarization. So once you measured one, you know what the other one was. And so instead of creating this state, Charlie, he measures whether this is the measurement outcome. And what you can see from this is that once Charlie measures, say, the psi plus state, it shows that Alice and Bob sent the opposite value. They sent the opposite bit value. One sent horizontal, the other sent vertical. But you can see both things are possible, so nobody knows who sent what. And that's the key of this protocol, is that all you're establishing is in which way were the two transmitted qubits correlated, but not what they were. So you can go through sort of a matrix here of looking at all the different possibilities of what Alice and Bob sent and what is measured. And as I said, we don't want the ones where they use different bases, so we skip the bottom ones altogether. And then we see that, well, if Alice and Bob sent Alice sent H and Bob sent V, there's a 50% chance of them measuring one of these. And they know that when they get this measurement outcome and they use this basis here, that they need to flip their bits because they're different. And so they can establish, just decide who flips the bit, and then they'll have a shared key. They'll know what the other one sent. But if you turn these around and say VH, it's the same result. But when one of them flips the bit, then it's the other value that they end up with. And for the other ones here where they have superpositions, there's also some probabilities that allow them to either do a bit flip or not a bit flip. And in the cases still, they can figure out between themselves what is the agreed upon shared key. And all that Charlie knows is that there was this correlation, but he doesn't know what each of their bits are, and so he cannot get access to the key. And that means that even if he goes, you know, sort of like rogue and becomes untrustworthy, he cannot get access to the key. And so for that reason, we call it measurement device independent, because it doesn't depend on who controls the measurement device. So this was done, this was proposed a few years earlier, I think around 2010, by a researcher from the University of Toronto, and was then implemented here a few years later, again, over a real-world link. You can see now there is still the link from U of C to SAIT, and then an additional one to the Foothills Medical Campus, because we need 2 senders and then a station where the measurement is done, Alice, Bob, and Charlie. Again, some publication came out of that. Nowadays, we're still working on that, and in terms of commercialization, this is the startup or spin-off company that we have, founded a few years ago, called QTI. And you know, one of the things that we're doing is that we're establishing these correlations over long distance using this protocol. But more broadly, the spin-off is about building quantum networks. So this can be used as a stepping stone to create a quantum internet. And this is, will find us over in the research park at the University of Calgary. Okay, then, continuing with the history, in 2013, something really interesting happened. We got these new detectors. They're called superconducting nanowire single photon detectors, or SNSPDs for those who don't speak too fast. So they are excellent in terms of 90% efficiency and very small dark counts, and they were a game changer in terms of what you could do, because suddenly now you could have a very large signal, every single photon was counted, and very little noise. So this was a severe limitation previously, and they're tiny. The only problem is they have to go cryogenic because they're superconducting, so we operate them below a Kelvin. But you can pack many into a single cryostat. This was done in a collaboration with NIST and JPL in the US. And so now we could do a whole bunch of new and interesting experiments. One of them was quantum teleportation. And this came about in a collaboration with the city of Calgary. So here's the link that we had. Oh, I didn't know it would cut it off here. All right. We had now different locations within the city, and I'll show some more pictures. One of them was right over here under the concert hall, Arts Commons. The other one was down at, what was it again? The data center down in M something, Manchester, there it is. And so altogether, we had these links. And so we did quantum teleportation, and we got at least a mention here on the front page of Nature Photonics, which is, you know, where people go to see. And so what is quantum teleportation? Well, let's start with what it's not. It's not this. Okay, not this, sorry. What is quantum teleportation? It's still weird. It's the disembodied, complete transfer of a quantum state. So even physicists puzzle with that, some of the famous ones, right? So disembodied means that no particle is actually exchanged in the direction that the quantum state is transferred. So it is a way to transfer the complete quantum state, which is something you can only typically do if you actually send a quantum system from one state to one place to the other. But in this case, it happens by, at the time that you do a measurement, and send the result of that measurement classically. Okay, let's see if we can illustrate what this means by a little use case. When might you want to use quantum teleportation? So here's Bob. Bob's earned some money somewhere in the, maybe in the resource business there, so he has a truckload of it, and he buys an expensive quantum device, you know, quantum computer or something really expensive. He loves it. It's very personal and important to him. And then Alice comes, and she would like to use this quantum device. And who doesn't trust a little girl with a shotgun. Well, Bob doesn't. He doesn't trust her. So he doesn't want to give her access, right? So what can he do? He still sees the business opportunity there for Alice. She's got some money too, and he likes money. In comes Charlie. Charlie, he's industrious, and he says, I have an idea. I'll facilitate the connection. And he tells Bob all he has to do is he has to install a source of entangled photons in his lab. And that source of entangled photons will take one of the photons to his expensive quantum device, and the other one he's going to send out. Notice that in this case, no information is going into Bob's expensive quantum device. So now he's more relaxed. I think he can do that. And that is what quantum teleportation essentially is. We end up in a situation where there is the Charlie's measurement here on the state that Alice sends to him, and part of this entangled pair that Bob sends to him transfers her quantum state into this device here, or onto this photon that's here. So that is actually what quantum teleportation is, and this is maybe one dreamt up use case of that. There could be others, but again, it has a lot to do with security. And, you know, she could enlist other users of quantum information. We're actually coming up to Halloween, so I guess it's very appropriate, right? So here's the quantum teleportation experiment, again, now with the actual location down in Manchester listed. And very, very, very quickly, here's what we did. We had these 3 locations, very close to City Hall. People outside of Calgary don't know. Then the Arts Commons building is not as easy to visualize. So these are, and I think this is just a generic building to represent the data center. I don't think it looks like this. So Bob has these 2 entangled photons that he then sends one of them, creates them in the lab. This is the setup. We call them B1 and B2. For those oldies will know what this is. And then we send one of them over the link towards Charlie. And at the same time, Alice prepares a qubit that she, or some information that she wants to transfer to Bob. They come together and they meet over at, oh, this is actually the location there at the, inside the data center. And they meet at Charlie, which was over in the Arts Commons building, and then he performs this joint measurement. And again, here's what that lab looked like down in the basement, just under the concert hall. And now the state has been transferred. And again, we use these superconducting detectors. Here's the cryostat, and here's the compressor for that. So lots of fun. Here's our moving business here, temporary quantum moving business, I guess. Again, everything in the back of the van. And now I was part of the whole thing as well. And, you know, here we are in the bottom of the basement, setting things up, trying to get things working. Have a little cart there in the data center and making all the people in the city nervous about what on earth are we doing there. And this does not look safe. But it was. So the aftermath, because what we learned is that, well, if you take Einstein and mention him somewhere and you put some science fiction in, akin to this, you get a lot of attention. And so this is the kind of attention we got, you know, most of it good, I think, you know, we were on the news, we became one of the top news stories from that year from out of Calgary, and, you know, around the world, it just kept creeping up with the weirdest of stories, you know, from all over the place. And this particular one here from MTV News, for those of you who know what that is particularly interesting because of the category that it was listed under, which, if you look up to the far left there, I thought was really peculiar. So who knew that that was a category? So all fun and games. Let's just circle back to this discussion about the distance. How far do you want to go? So if you're going over not so long distance, so let's say you're within 100 kilometers, about 1% of the light is going to come through just because of the attenuation through the fibers. And we can live with that, you know, 1% loss. The way that quantum communication protocols are set up, you know, of course it's going to reduce the probability of your light coming through and your rate of exchange of information, but it's doable. But if you go to much longer distances, let's say you go somewhere above 2,000 kilometers, here's 2,000 kilometers as an example, your transmission becomes ridiculously low. You can wait something comparable to the age of the universe for a photon to come through. So that's not quite acceptable for most people. So we need to find some other ways to do quantum communication in those ways. And there's a couple of different approaches. If you want to go really long, there is a cheat sheet. The cheat sheet is to build a network that's made up of nodes that decode the information from the quantum realm into classical and then back into the quantum realm. But you have to trust these nodes, because if somebody takes over that node and once the information is classical, it's all accessible, well, then you have a problem. Somebody could steal it, you know. So where do they implement it to the largest is in China. So they have this whole backbone network of quantum links, this trusted node network. And the one thing you could say about that is that, of course, it is a stepping stone towards a more broad or more general quantum network that doesn't rely on trusted nodes. You put in some of the infrastructure and it's ready. And other places in the world, same approach is used as sort of this stepping stone. Another thing is to change the way that the loss occurs. So instead of having this scattering loss that causes an exponential decay of your signal, let's try to work with a different kind of loss. And where we don't have loss would be in a vacuum. If you send light through empty space, it doesn't scatter, it doesn't get lost. And so where do we have vacuum? Well, 10 kilometers or 50 kilometers up, we have more or less a vacuum. It's called space. So that's the notion behind space-based quantum communication. The only loss you do have is the fact that all beams expand. So if you have a beam, its mode, its size will expand, and that of course looks like you lose some of the light because it's not hitting your detector anymore. But that goes with the square of the distance, because the area grows with the square of the distance. So that's much better than exponential. Realizing that, we come back to the Chinese. They sent up the Mishi satellite in 2016 or 15 and published a whole bunch of stuff on that. You know, lots of groundbreaking experiments on quantum communication, entanglement distribution, and they have a network of these ground station and satellite ground station. And so we said, well, we should have some quantum networks ourselves. In fact, the Canadian quantum satellite mission, which was led by, or still led by, University of Waterloo, was started even before the Chinese started theirs, but things just went a bit slower here, and funding didn't come quite as fast. Here in Calgary, we also would like to be part of that. We're building an international quantum network. Well, you'd want to have ground station in many places, not just in Eastern Canada, but also in Western Canada. And here's our ground station. Here you see an example of how it operates. This is actually the Chinese satellite, because that's the only one that's up there to practice with. The green light there is that one, and it's shining down a beacon laser, and we're shining up a beacon laser. And according to Star Wars mythology, we're actually the bad guys in this case. So I don't know if that's on purpose or not, but you know, okay, we'll live with it. So here's what happens during a quantum satellite pass. You have the satellite coming up towards the horizon. You shine your beacon laser in roughly the direction where you expect it to come. It shines it down to you, and then you intercept. You lock on. It's like a camera. It's like following a moving star. And then you start exchanging the quantum signal at a different wavelength that you can split off. And so if you look at, you know, where a quantum satellite ground station was, it was at the edge of campus. They started constructing a whole bunch of things, so we had to move it. But we moved it out to this beautiful place, which is the Rothney Astrophysical Observatory. And now we're up there in our own little building. And here's an example of a pass where we can see how, as time goes by, we have a spike in the number of counts in the quantum detectors that we get when the satellite is the closest, and then it goes down again. And using that, we can do the analysis, and we can start to extract, you know, how much key we get. These may be all, you know, mystery words, but we get 167 kilobytes of secure key, which can then be used to expand a key for actual communication. And here's a Canadian quantum satellite. which Catania is also involved in. And I don't know, 2025, is that a reasonable estimate, I think, is for the launch? Scheduled for 2025 sometime. So, and we'll be serving as one of the ground station of that. So that's where, one of the newest things that we're working on. And then the final sort of few slides here will just be to discuss the medium distance. What if you are sort of less than 2,000 kilometers? You don't have to go across an ocean, but you're not within a city. Well, the losses are still too big to go straight through an optical fiber, but you don't want to use satellites. I'm used to thinking, I come from Denmark originally, and it's like gray all the time. There was one November where I didn't see the sun. It's kind of sad. But then I came to Calgary, and everything was bright, and I thought there's always a blue sky. Then we bought the Quantum Satellite Ground Station, and there's so many times that this little thin cloud layer just lingers up there, and it blocks your satellite link. So, I have my doubts that it's going to work for everything, and certainly if you can avoid it, because the distances are not too large, it's better to look for alternatives. And that alternative is called a quantum repeater. For those of you who are in telecommunications will know what repeaters are. They're amplifiers, but we can't amplify quantum states, so we have to do a different thing. So I won't go through this because that takes too long. Even a minute or 5 won't do. But the quantum repeaters relies on these kinds of measurements, joint measurements that I talked about to establish correlation, Bell state measurements. And they serve to distribute entanglement over from small distances, sort of daisy chain it onto a large distance. And what the Bell state measurement is allows you to synchronize this process. But it also requires sources of indistinguishable entangled photons, and it requires a very, very different task of devising quantum memories, things that store quantum states that have been transferred from the light for resting there for a long time. Now, this leads us to the last 3 slides here of other things we do, and a lot of stuff we do in the lab as well is quantum memories, specifically aimed at this task of storing the quantum information. We also do a bunch of other things like post-processing for quantum communications, do some molecular lanthanides experiments. We do biophoton detection because it's about detecting very weak photon signals. We work with microwaves to convert the optical signals into quantum signals that are compatible with superconducting type quantum computers. And we started also using nanofabrication facilities so we can make really small things and not just do big bulky things. And final slide here. This is us from not this summer, but the previous summer, enjoying the blue sky in patches, and also this is always good for attracting people to come here. All right, so that's all I have for today. Happy to take questions if you have any. Yes. Should I bring this one over?
What is next for you and your team in application, in experimentation and application?
Yes, so there's a couple of things. We want to connect to the quantum satellites, the Canadian one, that's the free space mission, demonstrate using Canadian resources, several protocols that will show Canada as a leader and Calgary is part of this interconnected network. I think the main challenges otherwise are on this quantum memory side. It's a very difficult thing to have the quantum information stay put and not be disturbed. As soon as you take the quantum information from light into electron states or spin states, those are all things that are sensitive to magnets and electric fields in their environment or from outside. So things don't stay quantum very long. It all gets mushy and blurred. And so keeping that safe is very, very hard. and especially in a way that also allows you to still interact with exactly the light that you like. So getting those memories to work is a key challenge, and that will allow us to build these quantum repeaters. So making those available will take the quantum networks from being viable only within city limits to something that could be viable, over longer distances. Let's say between Edmonton and Calgary, or even all of the prairies, something like that.
All right, another question. So, how are you funded through the university? Do you how do you get people to take a chance on something so theoretical and then to come up with practicals and practical solutions?
Well, it's funny that you say something so theoretical. I mean, you should see theory, real theory. That's a completely different ball game. I would say that I think there is of course the potential that everybody sees for this. Of course, a lot of people and funders will also see the risk involved in how long is this going to take us. The funding, to be very specific, is through provincial and federal grants, where there's lots of opportunities right now. The federal government has a quantum strategy, national quantum strategy, since a couple of years, which injected a lot of funding into this area to develop it, both businesses and academic research. And the province of Alberta has been very supportive as well, has seen quantum as being one of the areas that really will drive diversification of the economy. So within Canada, the two provinces, very interestingly, that are sort of pushing quantum the hardest are Quebec and Alberta. And we're actually collaborating, who would have thought, right, with Quebec a lot and people in Quebec on building these quantum next level quantum demonstrators.
Right, and the UFC's been really good at spinning off businesses out of the research there. So I mean, you've seen that with QCloud, but are you seeing that the industry partners looking to partner, are they ready to get to invest in the work that you're doing?
I think that would be a good question to also ask the Quantum City team. Because Quantum City really has been about looking at the application side instead of just so is it bottom up or top down? Yeah. And I think that top down, I would say, where the application experts are looking for solutions and they just start hearing about quantum. And that's where Quantum City is about facilitating that connection with the use cases. Whereas the academic part has been very strong for a long time, I would say. As the Institute for Quantum Science Technology, I think it's 2002 that it was instituted at the university.
Great, David. Did you have anything to add on that? You're good. Good.
I saw
Brett.
a hand down there.
I'm kind of curious. I love the turtle with the shell. From the communication side, how would you rank or rate the resiliency of quantum communication?
I mean, I think as we're developing these systems to be more commercially ready, we of course become, as physicists, acquainted with a lot of considerations that we never thought about, how do you secure your whole stack and not just this physics part, right? And I think, of course, as physicists, we could never do that because we don't have the know-how. And the nice thing is about when you start to spin off things into companies is that it enables you to now build a team that has this expertise. Within the universities, like I work together with computer scientists and people from engineering school, but it's always hard to get students between them. I get physics students when they apply for master's and graduate degrees, not engineering or computer science students. So in a company setting, it's much easier to get this whole ecosystem or hold this whole level of expertise on the different parts of the stack together, and then secure this aspect, what we would think are not the novel parts, but are important parts to do right. The quantum aspect of it, I think the protocols obviously are secure, but again, loopholes come, and we have to, just like with any system, we have to protect those loopholes. And I think it's mainly in the context of quantum computers being able to, or maybe some sort of algorithmic advance, being able to erase all kinds of security. It's not like patching a small hole, which is some security breach in a software or some backdoor. It's about the whole basis of our encryption infrastructure being broken. That's what this is supposed to safeguard against. And of course, there's still going to be patches here and there that we have to plug. That will not go away. And people are going to be inherently unreliable as well. They still will be.
That's great. Okay, so I think Daniel, you're joining us on the panel as well,
I believe so, yes.
and we'll see you at 12:05.
All right, so welcome back to Quantum Discovery Day at the Wave at the City of Calgary. Very excited to have a special panel with me today of all of... Oh, yes, sorry. Sit on the couch. Hey, Dave. So we have a number of people who are very active in the quantum ecosystem here in Calgary. And Calgary has been known as being somewhat of a tech hub, and Alberta as being known, and we're on the map for tech now. And so here with me today, we have some of these experts that are prominent in the quantum industry for various roles that they play. And we're going to take some time to get to know them. So I'm going to ask a question. And before you answer, if you could please introduce yourself, give us a little bit of your background, as well as your organization and the role that they play in the ecosystem, I think that would go very well. So can you each explain briefly what quantum technology is and why it's considered a game changer? How about we just pass the microphone down? Sorry, Dave.
Just full disclosure, I'm the last addition to this panel. So my name is David Yiptong. I'm with Quantum City, but I also work with Kai Ventures. Kai Ventures is a quantum ecosystem builder based out of Switzerland. They also have a bit of a VC arm, so they can actually invest in early stage companies. We have an accelerator program that's coming to the Quantum City facilities in March. So if you know any companies or entrepreneurs, applications are open. As far as what is quantum technology, looking at who's down the line, I'll let them actually talk about it because I am not qualified for this. But in terms of how it's game changing, I think it's I was just talking to Brent in the crowd here about how technology changes how we do things from a business perspective, but even socially, right? And we'll see the effects of that social experiment in a couple of weeks with our neighbors down south. So. Quantum's going to be a big game changer because it's one of those things. It's kind of like I was talking to Brent about the CBC posted this really old piece about the advent of cellular in 1980. And in 1980, people had no idea what cellular was going to do. And if you think about how dependent we are on that right now, 40 years later, we can't live without it. But they were talking about then about how they had no idea what the business model was going to be for this, but it was coming. So similarly, we're at 1980 now for quantum. 40 years from now, we'll be sitting here going, do you remember when we didn't know this was going to happen? So I think that's why it's a big deal. But this guy next to me can tell you what quantum is.
Well, thank you. Thank you for your trust. I'm Daniel Oblak, associate prof, the University of Calgary, which is a post-secondary. Oh, you guys know that. What is quantum tech? I guess I will take it from the other point. So you said what it can do, right? So I think even within this community, there's a bit of a discussion about what is quantum. When you inject $350 million from the federal government into a field, it looks like just about everything is quantum, just like everything is AI these days. So, it's actually a bit of a controversial question in some sense. But if I were to say what is quantum, what really is quantum technology, it's when you use very unique quantum mechanical properties of systems to do something that could not be done without those quantum mechanical properties. So, the superpositions as we saw it, the single quantum system level ideas or entanglement, those are sort of the hallmarks of what is quantum. In some recent applications from the National Research Council, there's actually a scale of quantumness where you can put your application in as how quantum is it. And if you use entanglement in your proposal, then it's the highest level of quantum. So we're getting there with the very specifics. So I'll hand over the mic now.
Cool. Yeah. I'm Adam. I'm a scientist in residence at Quantum City. So my job is sort of an interesting mix of research and industry outreach, industry engagement. So Quantum City is really trying to reach out to the non-quantum industry and get them excited about quantum, interested in quantum, and to bring projects from them back to academia or to quantum solutions providers to execute and to really build an ecosystem surrounding quantum. And the question, what is quantum technology? What's exciting about it? I think Daniel said, almost exactly what I was going to say, which is a good sign. But I'll just add, the excitement, and this is me speaking as a scientist, really comes from the fact that quantum technology is about the chance to do things that are impossible classically, impossible any other way. So there's a, I think about algorithms and computer science a lot. There's problems that we can only solve with a quantum computer. The only way to answer this question is to build a quantum computer and then run the problem on it. And so for me, the excitement really comes down to the fact that we're trying to do things that would otherwise be impossible. And that's what motivates me.
Thank you, Adam. Hi, everyone, again. I'm Dr. Katanya Kuntz. I'm a research associate at the University of Waterloo. So Daniel mentioned during his talk the KeySat mission. I have a role there. But here I'm representing Cubo Consulting, and I'm the co-founder and CEO. With Cubo Consulting, we are trainers and translators and consultants on what is quantum tech. I use my background of experimental quantum optics, and AJ uses his background of education and business to translate these technologies to literally anyone. And why I think quantum tech, or what it is and why I'm excited, it's like I said, quantum 2.0, it's the addressing of individual particles, individual atoms. So now we're using particles of light, photons, things like this to do the technology. And so it's beyond what our current classical technology does. And it's very exciting, especially from what we've already heard. There are problems that are just impossible to do classically. And when we use a quantum system, they now become possible. Oba?
I'm sure I can top that. Yeah. Hi, everyone. My name is Oba Harding. I manage an innovation ecosystems group with Prairies Economic Development Canada, or PrairiesCan, as we're known for short. My background, I think, is a little bit relevant here. I come from a scientific background. I was a biologist. I worked in reproductive medicine and fertility. After that, I worked in research and development funding for quite some time, and that led me to my current role with PrairiesCan. At its core, we're an economic development agency. We are responsible for promoting and developing the growth of the economy in the Prairies provinces in Canada. And that's a good preamble to why we are interested in quantum technologies. Big investors and supportive of the quantum ecosystem and Quantum City. What is quantum? This is a fun question. I was talking to my 10-year-old last night. And I thought, if I can nail it here, I may have a chance tomorrow. I guess my explanation of quantum is a fundamental technology based on the quantum mechanics and physics that, without diving too much into the science, allows us to do things and explore questions and equations and problems in a way that is much faster and allows us to address complexity in a way that we couldn't even conceive of previously. I know that's very high level, but that's probably the easiest way that I can leave it at. But then the biologist in me thinks, or sorry, actually before I jump to that, I'll say the economic developer in me thinks the quantum technologies are very interesting and captivating of the mind, but really what we're thinking about is the applications. As an economic developer, I want to know how companies, big and small, can take advantage. How can we save money? How can we save lives? How can we save time? And I don't know about you, but I feel like our world is getting increasingly complex. So there's no shortage of complex problems. And to have tools with which to rely upon to address them gives us a framework to move forward. We can't just be stuck. Climate issues, the ability to sense and even be aware of phenomena and matter around us, those problems don't go away. So quantum will give us a framework with which to understand these things to an extent and then address them. We'll get into applications later, but then I was going to say the biologist in me always thinks of where we're going in terms of healthcare and personalized medicine. You may have a genetic disease or disorder that's attacking you and your DNA in a very specific way. Quantum tools and how we can approach that with drug discovery and how that will interact with your DNA and your molecules or someone that you love in your family, friends, or particular circle, those are powerful tools that allow us to move forward and make progress towards those. So I'll cut it off there.
Thanks, Oba. Hi, everyone. My name is David Basto. I'm with the City of Calgary. So I've been working with the City of Calgary for close to 30 years now in the IT department. So I have a lot of experience coming up with solutions for different business units in the city, mainly around their networks, but also trying to anticipate some of the technologies that are coming down the pipe and learning to adapt to those technologies. So what is quantum for me? Quantum for me is a disruptive technology, a disruptive emerging technology that can be consequential for the City of Calgary. And we want to look at the risks that quantum can present, but also the risks of not doing and preparing for the emergence of quantum in our society. I look at, I'm hearing a lot of the experts talk about quantum and saying that, our classical perspective of quantum isn't quite right, and that we built our cities based on that perspective. And how would we build our cities in the future if we really understood what quantum was about? Would we build it differently? So those are a lot of the questions that we need to answer. And we need to answer, how do we start the journey of understanding quantum? What does that education look like? Because we do have a gap in education in understanding the need to look at quantum and the path to move forward with quantum. So I'm really excited about quantum. I think especially the risks in terms of encryption, I would like to see the City of Calgary be very prepared for that day when quantum computers become commercialized and we can still secure our data. Yeah.
All right. Excellent answers from all of the panelists. Thank you all very much. I heard making the impossible possible. I heard disruption. I heard utilizing special properties that exist on that scale that don't exist in the real world, in the regular macro world. Excellent answers. So I should introduce myself maybe a little bit. I'm AJ Sikora, co-founder and chief learning officer of Cubo Consulting Corp. Catania is my partner. And so my background is in business as well as education. And so I'm a communications expert. And so I'm really, really good at translating difficult, dense topics into regular English that everybody can understand. So let's move on to our next question. So next question, you know what, Dave? I'm going to take it easy on you. We're going to start at the other side this time. So How close are we? This is perfect for you, Dave. How close are we to seeing practical, everyday applications of quantum technologies in municipal services such as water management, transit, and corporate security?
Well, actually, what I'm learning from you guys is that there is some deployments in municipalities already for optimization. So that's really important because I think the city of Calgary or other municipalities as well offer a wealth of use cases where this technology can be tested and evolve. And so, yeah, I mean, Calgary has a lot of optimization opportunities in all the different business units, from water, transit, roads, traffic management, even IT, right? So, yeah, lots of opportunity.
Excellent. And would we like to continue on? This question is for all of the panelists, I was thinking.
Sure. Oh, well, sorry for, we can pass it back then, but I'll jump on this really quickly and say, yeah, I'm excited to hear the enthusiasm. I'm excited about quantum and what quantum can do. And an important part of the story that I'll say now, because I try and say it whenever I get the chance to, is that the path to finding a quantum advantage it has to be a back and forth between the use case, between the industry, between the quantum solutions providers, and also a feedback as the quantum technology itself gets better. So, how close are we? Close, but that doesn't mean that the first thing we try is going to look impressive or look exciting. It's really about starting the process by trying something, seeing what happens, and then iterating from there to sort of converge to an exciting use of quantum. So now is the right time to start, is sort of my feeling.
I totally agree with you on that one, Adam. Who'd like to follow?
Sure. I would just add that there are some municipalities that are engaged in quantum technologies around the world. So like earlier, I presented a use case from Japan. Japan has been a part of quantum technologies for a decade or more. And so there's also in Chicago, for example, and New York, there are fiber optic networks that are already established, and they are working on entanglement distribution. So we heard from Daniel that if you want to make a quantum network, you need to distribute what's called entanglement. And so all of these infrastructures are being created not just for public citizens, but also governments, embassies. Because often, for example, military, police, RCMP, they may need to communicate encrypted, and our current encryption methods are vulnerable to hacking. As you've seen in the news, especially over the last 5-10 years, there's more and more AI-driven hacks, and they are very good. So, and with the quantum side of encryption, it is theoretically secure. So yes, your physical implementation might have some vulnerabilities. That's why I'm an experimentalist, and I help you figure out what those are. But theoretically, if you can do it correctly in real life, it should be secure. And so I'm really interested in incorporating that, that security into the IT.
Excellent. Anybody else like to weigh in? I've got more questions. Let's do more questions. Okay, so this one's on funding. It's not specifically to you, Oba. Anybody can answer this. What types of funding and support are available for businesses and municipalities looking to invest in quantum technologies?
Yeah, so I wouldn't couch this as exclusively quantum funding, but really I think what we're talking about is innovation funding. It's particularly relevant here, and kind of looking up hotbeds of where we are seeing quantum activity. It tends to occur in cities or regions where we have high degrees of innovation, particularly in links to post-secondaries, but also where we see high degrees of entrepreneurship. And all of us here in the city of Calgary, I think we're seeing a lot of that. The funding, in this case, we're talking about largely public funding from government sources, but private investment is a key piece of that as well. One tends to catalyze the other. So The innovation funding, we've got a bunch of sources. So I said that Prairies Can, we are, of course, one option for that. We do innovation ecosystem funding. The way that I often describe it is there's kind of two ways that we can support that. One is direct to companies. We can always invest in companies, and we do. But that funding is competitive, often it's scarce. We also invest in companies indirectly through ecosystem programming, things like accelerators, incubators. There are industry associations, or I'd say partnerships with post-secondaries. That is a huge source of funding. There is I was going to say NSERC, or National Science and Engineering Research Council, NSERC. NSERC is providing significant amount of funding through some of their platform programs, through partnerships between companies and post-secondaries. That's not exclusive to any one post-secondary. It's available across the board. There's an organization called MyTax, who is best known for their collaborative internship programs. MyTax alone is providing $40 million in quantum-related funding for partnerships across Canada. The National Research Council, I think it was mentioned previously, NRC is also providing a significant pot of funding. There's a key message, though, I would encourage everyone to take away, though. Quantum is an incredibly complex and rich area. I don't think this is the kind of thing, as companies, big or small, that you dabble in. I think the pathway here is through a post-secondary partnership. Why ignore the resources that are in front of us? And that's why I think we see such heavy funding through the post-secondaries. There's an opportunity there, not just to access the funds and the outcomes, but to build prolonged partnerships, have those discussions, tap into research and development, tap into expertise. It's kind of a shared objective. So a lot of funding sources through post-secondaries, but then again, from the innovation objective. When you come at it from that slant, I think what you'll see through the NRCs and some of the federal departments is it's really kind of sector focus. So we really have to kind of understand what are our use cases, whether that's quantum computing, or whether that's an IT related or part of a larger digital transformation that we're all undergoing. But then we see a lot of applications in sensing. We have kind of remote sensing companies. I've seen applications with respect to methane or remote gas sensing, but we can also use this sensing for water within municipalities and other aspects. So there's a lot of different ways you can go, but I'll stop there.
And I'll follow that up with David from Kai Ventures. So how is Kai Ventures supporting the ecosystem, because they're involved in funding as well as part of the accelerator?
Yeah, Kai Ventures actually will invest in early stage quantum startups. The key is that they're looking for startups that are not just doing research, but that are trying to look at some sort of adoption path. And I think that goes back to like what Oba was saying and what Adam was saying about how you really need to have a problem that you're solving, and there needs to be this feedback loop with industry. So yeah, the Kai Ventures team is there. They're actually backed by a family office out of Europe. And this family office has basically decided to invest in quantum because they feel it will be highly impactful on humanity going forward because it's so foundational.
Excellent. Thank you very much. So next question I'm going to ask is for everybody, and I'm going to ask about cryptography now. I'm going to switch gears here a little bit. So how can quantum cryptography enhance corporate security measures, and what should businesses be doing now to prepare?
Well, it landed with me, so I'll take this one. Yeah, so that was a lot of questions in one. What can quantum cryptography do? Well, quantum cryptography can secure what you're used to doing right now when the floodgates open, sort of, for quantum computing. So, you know, it's always hard to sell or prepare or argue for a risk, but it is a risk. You know, we don't know exactly when quantum computers are going to come around fully, nor exactly when they grow to the scale that they will threaten quantum cryptography, standard cryptography, but no, it's going to happen. And then we have certain solutions that don't rely on quantum mechanics, which are the post-quantum cryptography, funnily named that. but there's still other harder mathematical problems. And then we have the quantum cryptography option. And I think, the right now we're finding ways to solve the issues with cryptographic, backdoors or hacks by patching up. But what we're talking about, the potential happening is that everything just becomes erased that we can do currently now. It's not just a small patch. It's like the whole thing, the whole wall breaks down. And then we have a real problem. And with that is what quantum cryptography I think is the final solution for that. There can be many steps on the way that goes through some harder mathematical problems, but eventually it is sort of the ultimate goal. What was the other part of the question? Or was there some more there?
It was, how can businesses start preparing now?
Right, and I think that's a very important thing to keep in mind. So I'm not a cryptographer or worked in security like that for any amount of years, but people who have a lot of experience within the business explain to me how long it takes to change over cryptographic standards, even though you're just changing, mathematical problems or computational parts. And we're talking about not 1 or 2 years, we're like 20, 30 years in some cases. So imagine now that quantum cryptography is where you want to go, and you need to have some changes to your hardware. You need to have some changes to your network stack. It's too late to even start now. I mean, but well, it's better late than never, I guess, right? So in that sense, it's important, right, to not just be complacent and wait for the quantum computers to be around in that scale, because once they are, then it's too late to solve the problem.
Just going to add one tiny comment onto that, which is that, not only is it too late to wait until the quantum computers are here, even before they get here, you should be worried, because there's this notion of a store now, decrypt later attack. So it depends how paranoid you are, but data you send on the internet right now that is encrypted, someone could be storing, waiting for a quantum computer to come along so that they can then decrypt this information and see it. So, if it's just me sending a message to my friend, I probably don't have to worry. But if you're sending something very sensitive, very secret, you should think about this. If you're sending the formula for Coca-Cola, probably measure now, decrypt later is a worry, or store now, decrypt later.
And I'll just add, in addition to quantum key distribution, there's also quantum random number generators. So I'm aware of use cases with the energy grid where they are incorporating QRNGs into the security system right now. So this is a commercialized device. These have been around, some of them have been around for 20 years, depending on what it is. And they can give you these random seeds that you can then incorporate into your encryption. So even though you don't have quantum key distribution, you could have some of that security from quantum in your current classical cryptography. And that might be a nice transition, because then you don't have to transition everything, you just transition your seed.
As mentioned before, I play in the innovation space, and I work with a wide variety of companies. Our team touches a number of sectors. We often talk about the digital transformation that's underway, and there's a lot of talk and of course excitement about AI in the last year and a half or 2 years. While I respect that, again, these aren't the kind of areas that you dabble in. We have companies that are venturing online in our country that are relatively uneducated about what they're dealing with, and if nothing else, the intellectual property, where they're selling the formula to Coca-Cola or everything else. You're talking about the secret sauces of your business, whether that's a business model or productization or so many other aspects. When someone wants to do a PhD, it's not the kind of endeavor that gets done in a couple of months or even a couple of years, and there's precursor degrees to this. My advice to companies is an awareness and education to dive in, if only for their own self-preservation. We've seen and experienced some of this conversation around cybersecurity. Quantum aside, are you even cyber ready? Do you know the degree of threat that you are under? And often the answer is no. And there is a cost to that. And I think in many cases, we often play the defense game. Well, it's not a problem today. It's almost like an insurance. We'll deal with it tomorrow. So I'd argue that the best time to start is yesterday. Little cliche, but the second best time to start today. I don't think it begins with quantum, depending on where you're starting from. I think it's just an awareness of where you are in terms of your cyber presence, access to your assets, to your clients' assets. And it's not always a matter of cost, but it's kind of that thinking of that adage of what's the cost of inaction. And so I think this is kind of a longer term plan, and it's one more resource. I can appreciate that on the size of your enterprise or whatnot, but the risks are huge. I mean, in layman's terms, as I understand it, as quantum cryptography comes online, it will render our current systems obsolete. I mean, like overnight, whoever has that has access to essentially take down governments, companies, and I don't think I'm overstating that. I don't say that to be a fearmonger. Yes, yeah, quantum computers. And so what we see in our world is this is being very heavily funded at the level of the state. China is outspending us by factors, by billions, really by billions. And so the concern isn't just for any one entity or any one country. I don't think us as a nation can do this alone. We have to have allies. We have to share research, understanding how municipal assets operate, if only for continuity of operations. There are some real threats here. So how do we start? I think it starts with cybersecurity and knowing that risk, but then how do we get to a place where quantum applications and those computing aspects get there? That can be, we can get there over time, but I don't think it begins there.
Yeah, very well said, Ova. Yeah, I would agree that cybersecurity is probably our biggest concern. Just like you were saying, Oba, it could be very quick onto us, and but there is that education process, and then there's the city can offer use cases to gain an understanding of how this technology evolves. So yeah, I think that if we can provide those use cases, we don't have to necessarily put a lot of actual funding, like cash, into this system. We can offer things like our assets and our use cases into the ecosystem to develop the technology. For instance, like our fiber optics. It doesn't cost us anything to give Daniel access to our fiber optics so he can, do his experiments. Similar, we can give them access to, let's say, the center to experiment with synthetic data, to create simulations that can test cryptography, right? So it doesn't have to be necessarily cash that's funding. It can be the opportunity and use cases that we can provide as well.
I just want to make a note about adoption and industrial adoption. I think industry and cities are really important in the early adoption of major technologies. When you look at historically, all major technologies are adopted by either governments or large industry because they have the capital. They can also amortize it over time. It's a different, But what's really important, and I think to what Oba was saying, when there's a new kind of trend, and when there's a new trend approaching us, to spur urgency, there's the use of fear. And I think we've seen this with clean tech and environmental initiatives. There's this fear that's used to spur urgency. But that's not really sticky. That will wax and wane. But if we look at it from a growth perspective, and I think in any city department, I think that the big message is that it doesn't matter what department you're in what company you work for, the next time you're doing a project, always think about, are you future-proofing it? I think Greg Hart talked about being future fit on Friday as individuals, but as organizations, how are we future fit? How are you thinking, okay, here's what we need to do, but then how do we future-proof this further down the road? Are there small things we can do now? Because I think then that takes the the intimidation factor out of, oh, is it quantum? Do I have to put quantum in here? Like, it's more like, I've got a problem to solve. I'm going to solve this problem today, but then if I'm going to solve it, what can I do to actually lay the groundwork for something down the road as well? No fear.
Excellent. Yes, and I'd like to follow up on that from an educational perspective. If you put a learner into a triggered state with, for example, too much fear, they shut down. They cannot absorb any more information, and therefore whatever education or whatever you're trying to sell, they're not going to hear it. So I don't disagree with using fear, but there is definitely a line of, hey, you crossed it and now the learner shut down. So thanks for mentioning that. I have an exciting question for you. We've got the City of Calgary. We've got some municipal services in the audience here. So what is the most exciting technology from your perspective that you would pitch to municipal services here at the City of Calgary WAVE?
I hate traffic. So, and in our neighborhood, there are these lights that are never timed properly, no matter what time of day you go through. And I'm sure this exists in every city, but this is a perfect optimization problem, right? So I would really love to try to help the City of Calgary improve your commute by quantum optimization. I'm just assuming you're going to say.
Yeah. No, it's funny. I was also going to talk about optimization. Same message, but a slightly different story, which is that, as a scientist or from a scientific background, I don't want to make promises. I want to focus on areas where I don't know what's going to happen. So I don't know how good a quantum computer is going to, if a quantum computer is going to be useful for optimizing traffic lights. But I would love to find out. And I would love to be involved in a project with the city in terms of finding out. And if it isn't, I'd love to be involved in the next optimization problem until we find one that works. So yeah, also optimization, but because of the uncertainty for me.
Daniel, you've got a comment. I know you do.
Do I? Oh, well, I mean, now the question is, should I stick with my own research or should I venture into something else? Well, let's stick with something I know something about. So, I think, okay, and I shouldn't use fear. Oh, gosh. I know.
Just a little bit of fear is okay.
A little bit of fear, okay, I've been approved. So, I think safeguarding the all of the data that's being transmitted through to control all of these utilities and the facilities of the city, from water to traffic to intersection traffic lights, transit, implementing a system that's based on an existing infrastructure that the city has, to select. Now, I would want to hear from the city, what is the first, the most crucial piece of infrastructure that you'd want to take care of first, and then deploying it to that one and showing that, now you don't have to worry about that one for a number of years, and then let's see how that works.
It's okay. You don't have to pitch, David. Yeah, thanks. Okay, so looking into the future now, let's say, 20, 30, 50 years, what timeline do you foresee for quantum technologies to become mainstream, and what steps do municipalities or municipal services need to start taking now to get there?
I'm just going to quickly say, think about, when I joined Quantum City and Kai Ventures, I talked to Adam, and I asked Adam, where are we, if you were to describe regular computing, where are we in that timeline? And I think we were talking about being late 1940s, early 1950s. We just came out of the Enigma machine, a mechanical computer. Computers are really, you have to be specialized. They only do one thing really well. They add really well. They don't do anything else really well. And they're very hard to use. That's 1940, 1950. And we're looking at it here from 2024, and we're looking at computing now. So that's that time frame. Think about wireless, right? Or think about internet. the time it evolved. The internet started in the 90s publicly, and it took till about, what, 2010, 2005 for it to become mainstream and usable. And now we can't live without it. So you can see the timelines are compressing. So when you ask where, in 40 years, this whole adoption is going to accelerate. So it'll likely be shorter than the sort of e-commerce and mobile adoption, and definitely not as long as standard computing, right? So it's close, but again, not to enact fear, but I think we could be sitting here in 20 or 30 years, thinking back to, hey, do you remember the early 2020s?
Yeah, sure. I'll give a date, which is a bold thing to do. But I'll say if you look at the quantum, so to give some background, quantum computers, like David said, are not great, and they're getting better, but they aren't. We have a vision of what they could be, a sort of theoretical vision of what a perfect quantum computer would look like, and we aren't there yet. And if you look at the timeline that's put out by a lot of sort of leading hardware companies trying to build a quantum computer, they're all converging sort of around the date 2030 as the year when they're promising that we will have a universal fault-tolerant quantum computer. But think of this as this is the dream. This is what we've been trying to build for a while. So you can pin that dates to your mind, and if nothing happens by then, maybe the hardware companies were wrong. This is possible. But another piece of the pie is that I think lots of academics would say, if you ask them, well, say I handed you a universal fault-tolerant quantum computer right now, what would you use it for? They would say they don't know. We have ideas, we have thoughts, but it's really hard, really, really hard to know exactly what you're going to use this machine for before it's even built and before you have it to play with. So we've got to build the machine, but we've also got to try as hard as we can to have this back and forth to be ready for the machine when it's here in our hands. And that's sort of the exciting thing about the next 5 years for me. Oh, yeah, of course. Oh, yeah. Well, actually, yeah, let me point this out. Is that now, if you're involved, now is a great time to be involved because you get to guide what these machines get used for. You've got a really outsized impact on the development of these machines, on the strategizing around these machines, the earlier you get in. So, yeah, I mean, if you want to use them for good, now's the time to push for that, and I assume we all do. But
I just want to jump in. I totally agree with you, Adam. If there's a quantum computer that has X, Y, and Z applications, if you want Z to happen, you got to start adopting now, because otherwise they're going to make X and Y, and you're going to miss out.
And if X and Y have a lot more money than you do, you can't
Exactly.
wait,
Yeah.
Thank you. Yeah, so to continue on what Adam said, I have an analogy for a quantum computer and where we're at and how we don't actually have one right now to play with, right? So as Adam said, we don't have a fault-tolerant universal quantum computer. That's the holy grail. We do have quantum systems that you can do computations on, and those exist now. So we do have some systems, but we don't have the holy grail. The holy grail is the thing that's going to possibly break public key encryption. That's the RSA encryption that you use for your online banking and all those protocols, right? So there are some encryptions that cannot be broken, classical encryptions that cannot necessarily be vulnerable to a quantum computer. It's just that one in particular, the public key encryption. That one in particular is vulnerable to a fault-tolerant quantum computer. But right now, we don't have any of these machines to play with. So it's kind of like you're trying to teach yourself how to drive a car, and you're learning on a tricycle. So you understand motion and braking and turning, but you have no idea about an engine and all the other things that go into a car, right? And so with our systems right now, it's really hard to predict in 40 years what is a quantum computer going to be able to do. But I will make this prediction. A quantum computer is not better at everything, and quantum sensors are not better at everything. There are some classical technologies that will probably still maintain into the future. It's just the really hard problems that we want to outsource to the quantum systems.
I'll add something quick in that it's been touched upon from a few different angles about the role of municipalities in terms of this technology adoption, but also creating the conditions for companies to know that they can take advantage. I think that sends a real strong market signal to our companies that there is adoption around the corner, that innovation isn't just buzzwords or, oh, this is a really fascinating technology, but that's for someone else. No. There's a huge conversation playing out within the government of Canada about productivity. We have an aging population. Our GDP isn't as high as it once was, so our population is running down. And this has been a 15-year plus problem in the making. Technologies can help address that, but really we need people who want to adopt them and who want to play and experiment, and the outcomes are uncertain. It's a bit ironic coming from me. I work for a government where this is essentially our job, where we have to proselytize to people to say, hey, we want to engage, but the outcomes are uncertain. There isn't always a well-defined ROI at the end of this, and we have to be able to look the 20, 30 plus years, and that costs money. Now, from a private investment perspective, those people will reap those rewards, but from government, there are some uncertainties there. But it's still critical for the city to play this role and then also tell the story of why. Like, what is the benefit to the citizens? I think there's an education piece where the citizens get to see that they are the heroes in the story and they benefit. They're either reducing costs or there's potential for market opportunities, private or otherwise. But that story needs to be told, and that help needs to be told as to why they're involved. Because otherwise it's a taxpayer argument, what the heck are we paying for, and when do we get to benefit? So it's not always a 2, 5, a 10-year ROI, but that return is there. But by the time you want to play, actually to the point of your earlier question, when is the best time to get involved? By the time you see everyone else getting involved and reaping the benefits, that's way too late. So.
I like what you said about knowing the why, and to your example about driving in a tricycle, I don't know if any of you went to school here in Calgary and went to Safety City. You did. So my daughters went to Safety City. It's basically where they take kindergarten kids, they bring them, they put them on a tricycle, and there's like a fake road network, and they're teaching them the rules of the road riding on tricycles. It's just south. It's at the bottom of Crowchild Trail somewhere, right? And kids go there to learn. And now again, these are 5 and 6-year-old kids on tricycles learning the rules of the road. They're not going to be driving until hopefully at least 9 or 10 years later, right? But it's important for them to be exposed to that environment early. So I think, Oba, to your point, and there's a different why. You're putting those kids in those tricycles in Safety City. Why? Not to learn how to drive a car, but there's other things they need to know. And I think similarly for industry adoption and things like that, it's really understanding, well, what are we actually trying to get out of this, right? And that's really the focus. Because there's a long-term benefit to having that knowledge and awareness.
Excellent. Thank you all for your answers. We've got about 5 minutes left. Do you want me to keep going, or do we want to open it up?
Let's open it up.
Let's open it up. Who's got a question in the audience? Sandra.
As you're talking, just a flood of thoughts were coming into my head, and particularly about the discussion of the ideal quantum computer. What are we going to use it for? What are the use cases, the best cases, adoption? So now I'm thinking, because I typically reverse engineer, taking what it is that we want to solve, the problem, reverse engineering that, utilizing AI to develop that proposal, if you will, into its most difficult state in order for the quantum computer to solve. So what does an ideal quantum computer look like in our current structure of knowing and where we want to go with it?
So I am aware that AI is used to help design quantum circuits for a future quantum computer. Is that kind of what you're talking about? How our current technologies can help plan and shape the future quantum technology, or?
Because there were several different points made. There were several different points made in the conversation. Well, what does the ideal quantum computer look like? What are we going to use it for? Does every business need to use it? And posing all these questions into a most difficult problem state for then the quantum computer to solve that problem or those sets of problems.
Right. Well, right now there's kind of a race going on, like which platform for a quantum computer is going to be the best, right? So is it with light? Is it with atoms? Is it with ions, superconducting circuits? Like there's like 15 different platforms, right? So we don't know yet which one's going to be better. We do try to use modeling to estimate, you know, would this one work better than that one in certain circumstances, but it's still very unknown. Did you want to add?
Yeah. No, I'll just add a tiny bit and say that, you know, you've hit the nail on the head in a way, which is that a lot of what we're trying to do now is take hard problems that we want to solve and distill them down into something small and hard that we think is right for a quantum computer. That's a lot of what we're trying to do in research and in these experiments and in this, you know, where we're trying to uncover these problems. So you're absolutely right. We use AI, we use human intelligence too. You know, we sit down and talk a lot and try and figure something out. But yeah, that process of discovery you're talking about is very much happening and is important and is necessary to sort of take these problems and find their smallest, hardest elements that are right for a quantum computer. And I think we won't, you know, we can do math, we can make predictions, but the best use cases, the best problems are going to be things that we discover by accident or through experiment once we have the machines.
I'll answer your question in the other way, which is we will never know what an ideal scenario looks like. Because when you think about, you ask about any technology that we use today, at the advent of that technology, did we know what the ideal was? Right? And I'll go back to this well-worn cell phone example, right? In that CBC piece, they were showing the big Motorola brick. That was their ideal. Like that was the optimal at the time, but they were already talking about, hey, in the future, and it's in the news piece, it might be as small as your wristwatch, right? But they didn't know. And to answer your question, will all businesses need to use it? I think quantum as a technology, yes. The answer is easy, it's yes. But how it's going to be developed, I think you have to take more of a product development and product management perspective on it, which is which technology rises to the top will be determined on which problems need to be solved and the quickest and where value is generated, right? So I think for us, or for people who are on the cutting edge of the adoption curve, is really being open to having those conversations and doing the experiments. And if you think about every technology, there's been a lot of failures along the way, right? So the willingness to accept those failures, and I know for governments and municipal governments, that failure can be tough because you've got a taxpayer base that's not really tolerant for that. But how a center like this, like the WAVE Center, actually allows for that kind of experimentation so that you can move the needle and learn more about what the product development cycle looks like, I think will be really, really important. But I'm trying to not answer your question that way.
Excellent. Well, thank you very, very much to all of our panelists, all of the experts that we have here in the Calgary quantum ecosystem. Let's give them all a round of applause, please. Thank you so much, Jason, and thank you to the City of Calgary Municipal Services and the Wave Tech Center for having Cubo Consulting here to present to you on demystifying the second quantum revolution. So I am AJ Sikora. I'm the co-founder and chief learning officer of Cubo Consulting Corp. And I'm here to explain in English what this quantum revolution is all about. So, welcome to everybody. You are all welcome here at this presentation. You don't need any special physics background or anything like that. This talk is targeted to business leaders and government decision makers. So please keep an open mind. Okay, if you want to learn something new, you have to be open to it. So just don't actively fight learning today. Okay, and please ask questions. I love it when people ask questions. It lets me know that you're paying attention, that you're interested, and you understand what I'm saying. So don't be shy. Don't worry. You can interrupt me. My background is in education and business, and so I feel comfortable when there are, there's noise going on, there's people talking, hands going up, and people are excited to learn. So don't be shy. So here's a look at what we're going to talk about today. In section 1 is the introduction. So it's an introduction to possible use cases. Then I'll talk about what does quantum mean, and then we'll talk about the areas of quantum tech. In section 2, that's where we'll talk about the implications for industry. Of course, we're going to start with the quantum threat. Then we'll go into industry impacts, and then we'll talk about the opportunities and risks that are coming out of this sector. And then section 3 is global quantum investment. I like looking at these numbers to see, hey, this is a real industry. There are real dollars being invested in this, and real technologies are coming out of this industry. Okay, so then we'll look at an investment map, so a world map of who's who in the quantum, and then take action. So we give you a bunch of information. What can you do with that? We'll give you some next steps. All right, so introduction to possible quantum use cases. So we say possible quantum use cases because these are the things that could be improved with quantum technologies. Some quantum technologies are available now, but most quantum technologies are a future future solution that we could utilize. So in the energy sector, smart grids could be improved using quantum tech, and we'll look a little bit more in depth at that. Agriculture, we could have crop management to optimize the allocation of resources in order to maximize the crop yield. In travel, transportation, and logistics, we could optimize delivery routes to use less time, vehicles, drivers, and fuel. So less resources means we would save money. Okay, and then in climate change, so it could be used to improve climate models for more accurate predictions of weather events, and that is becoming increasingly more important as we notice the changing in our climate. Okay, so looking at the energy sector. So the problem is to improve smart grid management using quantum technology. So we would like to improve the production of energy, the distribution of energy, the consumption, and then of course we want to look at the security as well. So here are some possible solutions. We could use quantum sensors to improve the measurement range, resolution, and sensitivity to help detect early signs of equipment failure and monitor grid performance and integrity. Quantum simulations could be used to solve optimization problems that improve energy distribution and storage efficiency. These problems are too complicated to run on traditional or classical computers because of the huge data sets and the number of variables that go into these problems. And then smart grid communication security could be improved with quantum random number generators and quantum key distribution. If you're wondering more about those particular technologies, stay tuned for Catania's talk coming up after mine. Okay, so what does quantum mean? What comes to mind when you hear the word quantum? Just shout it out. Don't worry. Don't be shy. Yeah. Some level? Yeah, like on the tiny. Yep. Yeah, excellent. Subatomic, yes. Sandra, I think you said that this morning too. Yeah, right on.
Dishwasher tabs.
Dishwasher tabs. Yes, Marvel movies, dishwasher tabs, televisions, those are all quantum, right? No. There's all these businesses and other technologies that use the word quantum because it sounds cool, but it doesn't necessarily mean that they're actually using anything to do with quantum in their technologies. Except for the Marvel movies. Those ones I think are legit. Yeah, that's a joke, by the way. All right, so quantum physics, if you're wondering, is the study of the smallest particles that make up our universe. So the smallest that any matter can get. You can't break it any further. You can't split it any further. So that is the scale, the order that we're looking at. And so why could it be disruptive? Because on that level, on that order of magnitude, when we get down that small, matter behaves differently than it does in the classical world, in the macro world, here, right now, what we can see and feel and touch and smell. Okay? And these special properties that exist can be utilized to create new and improved technologies because they exhibit characteristics that we couldn't use in our classical technologies. So that means that if there's a new way to do something, that opens up opportunities and possibilities. So some of the areas of quantum technology that are being commercialized right now are quantum computing. Within quantum computing, we also have quantum optimization. There is also quantum simulation. So a simulation is, say, simulating an environment that has a number of variables and parameters to be input. If we have too many variables and parameters, we can't do it classically, so we need a quantum system to run that simulation. And so people are exploring utilizing quantum systems to simulate nature or other environments. And that can be very handy. Then there's quantum communication. Quantum communication is theoretically 100% secure. So that's an important technology. And then we look at quantum sensing as well. So quantum sensors, more precise and more sensitive. And then quantum random number generation. And as I mentioned, Catania will talk more about that one as well. Okay, so let's move on to section 2, implications for industry. This is what businesses really care about. This is what government decision makers really care about. What are the implications? So let's start off with the quantum threat. Put up your hand if you have ever heard of the quantum threat. Okay, yeah, Adam, I wanted to see your hand go up. So quantum computing is exponentially more powerful than classical computers. And it is expected that a quantum computer that is powerful enough to break encryption standards will come available in maybe 5 to 15 years. There's no set timeline. Maybe 2030, maybe. I heard somebody say Pi 2025, I think. It was like, this was a couple years ago. It was like 3 years out and they were like Pi Day and whatever, and everybody laughed. And anyways, so the general consensus is about 5 to 15 years. We don't really know. It could be sooner. As we've talked about on our panel and earlier today, the rate of acceleration of technological development is increasing. And that means that it makes it hard to predict these things about when specifically something will come online. But it's about 5 to 15 years. So if we had a quantum computer that was capable of breaking our encrypted information, we wouldn't have to worry about that until the future, right? True or false? False. True. Well, you're the quantum physicist, so okay. So no, she's right. False. We do need to worry about it now because of this threat right here called harvest now, decrypt later. Sometimes people call it handle, HNDL, handle threat. So what that is people could steal, threat actors could steal encrypted information today. Maybe your healthcare data, maybe your banking details, I don't know, something with a long lifespan on the information. So If they stole that information today, they couldn't access it because it's encrypted. However, they're holding on to that information. They're storing it in a hard drive somewhere in a cave. It's not connected to the internet. Okay, can't access it, right? They're saving it until they have a fault-tolerant quantum computer, until they have a quantum computing system that is capable of breaking that encryption. So that means that there is a threat today. There was a threat yesterday, actually. But I just want to make everybody aware that this is something that is going on right now. It is expected that threat actors are stealing encrypted data, they're storing it, and they're waiting until they have a computer that can break that encryption. So we'll talk a little bit more a little bit later on about what types of data they might be stealing. Okay, so let's look at this industry, data security. It follows the quantum threat nicely. So data security could be impacted because of this quantum threat. There are large implications of this because the time to prepare was yesterday. People could already have my encrypted data and they're just waiting to decrypt it in 5 or 10 years. Okay. One thing to factor in is the transition time. If you want to prepare for a post-quantum threat, then what you need is time to prepare. Because if you want to switch over a cryptographic system, it'll take you a few years to figure out which system are we going to go with, how is that going to address this threat, and then there's how much money is it going to cost? Where is the money going to come from? Then how long does it take to actually transition the technology itself? How long does it take to train your team to prepare? And how long does it take you just to find out what cryptographic assets you even had to begin with so that you can start this whole process? Sometimes that is a huge process of a few years. For a large organization, that could be a number of years just to find out what assets you have that should be protected. However, there are solutions, okay? I don't want to leave you guys on a cliff here. No, there are solutions, don't worry, okay? So there are two solutions right now. So one is called post-quantum cryptography. So that's using classical systems that use more robust algorithms that are expected to be resistant against a quantum computer as well as our classical computers, okay? Now, the issue with that is we don't have the fault-tolerant quantum computer just yet, so we can't test these against an actual functional fault-tolerant quantum computer. However, we do have suggestions. All right, the US government, NIST, released 4 cryptographic algorithms, I believe it was in August, maybe it was September, I can't remember. But they recommend those algorithms to be used in post-quantum cryptography. Then the other solution, which is actually a quantum solution, is called quantum key distribution. And this is 100% theoretically secure. So I know Daniel spoke about this. So in a system like this, it's theoretically secure, but in practice, there are a number of complexities that go into the system. And the other compounding factor is humans. You're always going to have humans in the loop. The next industry we'll look at is manufacturing. So quantum could offer a couple of solutions for manufacturing. One of the most exciting ones, I think, is in new materials discovery. So if we had a quantum computer that could simulate a natural environment, we could simulate new materials. We could say, okay, I'm looking for a material that has a certain heat resistance and a certain strength or compression strength, and you could test it all in simulation before you produce it and test it in the real world. It's not going to entirely remove that R&D aspect of the development process. However, it could significantly reduce the amount of time and resources that need to be dedicated in the research and development of new materials. As well, we could look at optimization to improve operational efficiency in things like production, logistics, and supply chain. The next industry we're going to look at is healthcare. And in healthcare, there are a number of applications. So using quantum simulation, much like manufacturing with a new materials discovery, we could look at new drug discovery in the healthcare industry. Also, enhanced diagnostics. So if we had quantum sensors that are more precise, more sensitive, we could improve our diagnostic equipment. As well, improved medicine. And I get excited about this one, the virtual doctor and treatment plan. Like, I'm not like, I know, we're not there yet. And it's scary thinking about it from this point here because I don't want a robot prescribing me medication or anything like that. But think to the future where all the bugs are worked out and you have an individualized care plan that factors in all of your health complexities, your genes, your things that you've inherited from your parents or whatever, and it factors in. Oh, you had this health issue when you were younger. You have this health issue now. Here is your optimal care plan, and then data security. So, healthcare data is the most expensive data that is sold on the black market. So if you want to talk about data that has a long lifespan that you would never ever want getting out into an adversary's hands, it's health data. Because if you have a general who has a peanut allergy, you don't want the enemies to know about that vulnerability. Okay, and then of course, travel, transportation, and logistics. So if we could use simulation to improve optimization to improve fuel efficiency, right? Maybe the routes could be optimized. Maybe you're the city of Calgary and every week you have to plow the roads 3 times and you want to do it as quickly and efficiently as possible. Perhaps quantum optimization could help with that. And then, of course, using quantum sensors, we could improve safety and navigation. And, of course, let's look at the finance industry. So using optimization, we could optimize financial portfolios and find the best way to get the greatest return with the least amount of risk. As well, in quantum communication, we could use quantum communication to improve authentication. So whenever we do a bank transaction, if you enter your credit card details there, you have to do an authentication, and that could be done using quantum systems. As well, if you're interested, there are publicly traded quantum companies that you can invest in right now. Okay? I'm not invested in any of them, but there are some amazing companies out there, and there are a ton, excuse me, there are a ton of startups as well, and lots of them are looking for cash. Oh, thank you. One sec, please. Yeah. One quantum second, thank you. Oh, I had a water right there. Okay, excellent. So the last industry we're going to look at, and perhaps the most applicable today, is municipal services. So these are some of the top areas that could benefit from quantum technologies, looking at multimodal transportation problems. So that's where you have goods or people, and you need to move them throughout the city using different modes of transportation: bus, train, car, bike. We had a bike in here yesterday that was used for delivering goods, right? Then there's waste collection, or same could be applied to snow removal, right? Although there are different complexities in those problems. Emergency services could be improved. Maybe the response time for a 911 call could be improved by a couple of seconds. Maybe it could be more. I'm not sure. We'd have to explore it though. And then data security. So there is a lot of sensitive data that the city has that could be protected using post-quantum cryptography or exploring quantum key distribution. And as well, energy storage and distribution. as I mentioned at the start of my presentation. And Catania is going to talk more about energy storage and distribution. Okay, so let's talk about the opportunities now. So get engaged with quantum so that you can start taking advantage of these opportunities. So you could gain a competitive advantage, do something better than your rival. You could prepare for disruption because these technologies are coming and they are disruptive, so you might as well prepare for them now. As well, there's the added benefit of finding new solutions. When you engage in deep tech and you explore new solutions, it makes your business more agile. You're better prepared to adapt to a changing environment. And we all know that the speed of change is increasing, right? So being more agile is a huge benefit to exploring quantum tech. And finally, you could be viewed as a first mover. So sometimes that inherently has value for certain businesses to be like, I'm adopting quantum, and everybody goes, oh, they were the first to do quantum, whatever, and everybody wants to work with them then because they're the first mover. Okay, and then there are risks, as I mentioned before. So there's the risk of data security, right? That a fault-tolerant quantum computer could break current encryption standards. Does anybody remember what the timeline was that I gave on that one? Excellent. Thank you. 5 to 15 years. Exactly. So that means we don't have to worry about it until 15 years from now, right? All right, you guys are all paying attention. Excellent, yes. And why is that? What's that threat called? Yes, excellent. Harvest now, decrypt later. Awesome. And there's also a threat that your competition adopts quantum, right? Like Tokyo. Tokyo's already, they've been doing quantum for 10 years. I didn't know that. Catania taught me that this morning. So, you know, if we want to get Calgary up to speed, we need to adopt quantum to compete with other smart cities such as Tokyo. All right, and then of course, there's the disruption, as I mentioned. So disruption is when we change the standard way that businesses do operations. So when we introduce new technologies, it has ripple effects. So if you introduce a new technology, now the business behaves differently because of that technology. Either they integrate it or they mitigate it or whatever it may be. But disruption is real. It's going to come, so you might as well prepare now. I don't want to scare you too much, though. This isn't too much fear, right? We were talking about that on the panel. All right, so the flip side to this is beware of the hype. Make sure that you know about the current state and what's realistic in terms of quantum technologies. So as I mentioned, quantum is a new technology. It's a very nascent technology. It's just emerging now. So some of these wonderful, fantastical things that I talked about won't be available for maybe 5, 15, maybe 25 years. It depends. And also, quantum is not magic. As soon as we get a fault-tolerant quantum computer, we're not necessarily going to cure cancer, solve world hunger, reduce climate change, et cetera, et cetera, et cetera. It's not magic. It's an iterative process. It's a technology. It takes time to develop. And we heard some really good things, I feel like, on the panel and in the other presentations today too, that we're talking about how you've got to adopt this technology so that you can build your solution. What solution does your business or your business unit want to see? Because there's limited resources coming out of the quantum industry, and they're going to go to the highest bidder. So if you're not ready to bid on their services now, they're going to develop somebody else's solution, and that person is going to benefit from this, and you're going to potentially miss out. If you wait until it's already commercial and everybody is saying, yep, I'm on the quantum train, it's going to be too late. All right, and now let's look at the final section. So the investment in quantum. I always love showing numbers. Everybody understands numbers. So here's the overview. So in 2022, global quantum investment reached $2.35 billion. In 2023, it dropped slightly to 1.2 billion. That was more of a reflection of the investment industry in general. And from the looks of it, other industries saw reduced investments as well during 2023. However, don't worry, 2024 is up there already. Now, if you're wondering about Canada, what are we doing as a country? Yes, they do have a strategy, which is amazing. Way to go, Government of Canada. It is important to develop a strategy and prepare for this because of all of the issues that I just mentioned. Now, over the last about 12 years, the government has invested about $1 billion into the quantum industry, and they now have a national quantum strategy to invest $360 million over 7 years. Then by 2045, it's estimated that Canada's quantum industry will be more than $139 billion and account for more than 200,000 jobs. So it's a real industry, lots of money getting pumped into it, and real businesses. Now let's take a look a little bit further at some of the companies that have raised. So this year, earlier this year in April 2024, we have PsiQuantum. They raised close to $1 billion Aussie bucks, and the government of Australia invested in it. It caused kind of a stir because then it's like, hey, how come you invested in them? And should we invest in one company or should we spread it out equally amongst all the companies? But anyways, Australia, they bet on one horse. And that horse is PsiQuantum. They're a quantum computing company, and they're part of the Chicago Quantum Exchange. They are the backbone of the Chicago Quantum Exchange, which I think means that they're just providing the quantum hardware for the computer. They might be involved in other things though too, like networking. And I'm not 100% sure, but I know they are quantum computing. Quantinuum, which is based in the US, they raised $300 million. And that is significant because that means that their valuation is $5 billion. Okay, so that means, you know, somebody invested a certain amount. They said, okay, I'll give you 300 million, and I get X number of shares. That means that if you calculate, okay, multiply that by however many shares there are, that means the whole company is worth $5 billion. That is a unicorn. So if you have a company that's worth more than $1 billion, they call it a unicorn. We already have quantum unicorns. Then there's Pascal, which is based in France, and they raised 100 million euros, and that put them at a valuation of about 400 million euros. And then here, we've got Canada on the map again. So here we have Photonic Inc. They raised $100 million US. And then Sandbox AQ, they're based in California. They're a Google spinoff, actually. That's how they raised $500 million. Big money going into these companies. Real technologies are being commercialized. This is a real industry. So here is the world map. I've summarized it over here, but thanks to our friends at Curica, they released this world map just last week, so it is all current information. But if you see the top 5 countries, we have China. They've invested $15 billion into quantum tech. The US is just shy of $5 billion. The UK is $4.3 billion. And then Germany is 3.3 billion, and then France is 2.2 billion. Canada has invested 1.1 billion so far, and I'm not sure, but we've dropped a little bit in the rankings in terms of quantum investment. Okay, so I've given you all this information. Now, what can you do with it? Okay, great. Well, first of all, I want to mention you don't need a PhD in quantum physics to get engaged in quantum. You can start by creating a budget for quantum, even just a small one. Just get a small, you've got a training budget, so why don't you just dedicate like a little bit of that to quantum training and start preparing now so that the transition isn't so stark. Ways to engage, well, you could explore novel solutions. You could trial a proof of concept. And you could also develop a quantum strategy so that you know exactly what trigger events are going to mean to you and what you're going to do in action to those. And as luck would have it, Cubo Consulting offers these services as well. So if you're ready to start your quantum journey today, you can get involved with Cubo to discover quantum solutions. We have a 4-week program to get your team up to speed on the quantum industry, and we'll uncover problems and match with potential quantum case studies. You could trial quantum technologies. That's about a 3 to 6 month program to select a problem, identify appropriate quantum vendors, and start trialing a solution. If you're ready and the trial goes well, implementation. So if you want to deploy a quantum solution and prepare team members for the transition, that's one of our services. And finally, strategic foresight. So develop a quantum strategy and a roadmap to plot your course for capitalizing on opportunities and minimizing the risks of a post-quantum economy. We also offer training solutions. So thank you so much for your attention. I hope that you all learned a little bit about quantum today. Do we have any questions or comments or discussion? Yes, sir.
Okay, so I know that there's different types of quantum computers, like the superconducting one or the photonic ones and stuff like that. I'm pretty sure China's like leading the way with the photonic ones, and then in Canada there's Xanadu and stuff, and like there's one right there. But is there like a benefit to one over another?
That is an excellent question for our technical expert, Catania.
Thank you for your question. So yeah, there are like 10 to 15 different platforms. You can use atoms, ions, light. All these different quantum computers have different advantages and disadvantages, and it kind of depends on A, the application, and B, the hardware. So for example, a quantum computer made out of light can talk to other quantum computers made out of light really easily because the light can go between them. If you have a cloud of atoms, it's really hard to drive a truck of a cloud of atoms to the other cloud of atoms so they can talk to each other, right? So even if you have an atomic system, you might have then light to talk in between them. So all of this is kind of up in the air. We're still doing the R&D in this industry. There are a few front runners that are easier to do. So for example, we're really good at chip manufacturing, right? Like we know how to manufacture computer chips. And so the companies that know how to do silicon chips, they've just been going smaller and smaller and smaller with their circuitry and with their transistors. Eventually they got to the atomic scale and things started to not work right? Because you started to cross over into that quantum realm. So now they make superconducting circuits, right? So it's still the chip manufacturers, but now they're making circuits that work on the quantum scale, but you have to cryogenically cool them. So like I said, there's advantages and disadvantages to all the different platforms. And if you want to know more, we can talk later.
Yeah, I would just add, so yeah, definitely, if you have specific questions, and we would love to discuss further to match specific, yeah. Oh, yes, okay. So, like, I'm a very serious guy. I don't know if you got that from my presentation, but we have a quiz here that will test you on quantum. It's just a little quiz, okay? And no, I'm totally joking. It's just for fun. You'll see. You'll get there and you'll be like, AJ's hilarious. So you can scan the QR there and you can take the quiz. See, I think I got 93. And I thought there was something wrong with the quiz, but then Catania took it and she got 100. So we knew what the problem was. Yeah. I was, yeah, totally. You know what's funny? This was actually Colton, our marketing guy. He came up with the idea.
But AJ did make kids love math, and so now he's helping people love physics.
It's actually easier to make adults enjoy physics than it is to make junior high students enjoy math. Yes, Sandra.
Am I correct in what I heard that you mentioned quantum key distributions are theoretically secure? 100%. What would make them insecure or unsecure?
As much as I'd love to answer that, Catania is actually a domain expert on quantum key distribution, so I'll let her answer.
Thank you. And I've done hacking experiments on QKD systems. So the vulnerability is in the physical implementation of these devices. So when Alice has to send light to Bob to make the key, Alice has to make choices. Alice has to decide what bits to send. That has to be random. If there's any kind of, pattern to that randomness, that's a vulnerability. Same with Bob. Bob has to make choices when Bob measures the signals. Bob has to make those choices randomly. If there's any pattern in that, that is a vulnerability. So there's a lot of vulnerabilities in like the randomness side of the choices. Then you've got the physical detectors. So we heard a little bit about that earlier this morning. The physical detector can be hacked as well. So there's a lot of these things, but that's why experimentalists like myself, we test these systems. We can actually find, can I hack it? Can I learn the secret key or something? Yeah. And I think based on the expressions, we've got some people trying this quiz, and it is funny, right?
Yeah. One word that I've kind of heard repeated over and over again, especially on the panel, was experimentation. And I think really like that's where you go from here. How do we move forward? We experiment. We try it out. We see what happens. We reiterate. We try it again. And I really like you saying that you're an experimentalist. That's what spurred my memory to think of that. But I think really like that's the action I should have put on the slide is experiment. One more question. I got time for one more question. Yes, sir.
So I suppose the quantum computer itself is a very advanced technology. So only a few top technology companies would have a working quantum computer. So like, is everybody else who is working on it, they have some access to those computers and for their computing power?
Yeah, so what we're seeing typically is people offer like quantum computing as a service, and it's like a cloud-based access. And so it's not a full fault-tolerant functional quantum computer, it's a quantum processing system. So it can do some processing in a quantum state. And so what that means is all of the information that goes into it is actually on our classical computers. And so we have to input those parameters. And so that's kind of where it becomes a little bit complicated. How do you take these really big problems and you translate them from classical to quantum? But typically what they try to do is you get all the information, you get all the parameters, et cetera, and then you do the actual processing with the quantum system. And so it can be accessed via cloud. And there are different models as well because it's an economy, and so there's people who do this, there's people who do that, and so some people are actually trying to sell like physical computers to people. Like I've had people approach me on LinkedIn and they're like, "Hey, do you want to buy a 1-qubit computer?" And I'm like, "What the heck can you do with that?" Like, but they're for educational purposes, et cetera, and things like that. Yeah. All right. Thank you very much.
So Catania is really going to get into how do we really apply some of these quantum opportunities to solving some of our community's biggest problems. I'll pass it over to you.
Thank you very much, Jason. And thank you again to the City of Calgary and to Dave for having us at the WAVE Tech Center. We're very excited to be part of this. So hello, everyone. My name is Dr. Catania Kuntz. I'm an experimental quantum physicist. Today, I'm going to bring a little bit of quantum tech to your world. So in today's talk, we're going to start off with what is the second quantum revolution, because maybe you didn't even know that there was a first quantum revolution and we're into the second. I'm also going to describe our Young's double slit demonstration. That's just over there in the corner. It's demonstrating some of the very basic properties of quantum, and so I'm going to go through some of the key takeaways of that demo. And then we're going to get right into use cases. So we've got quantum computing use cases. We're going to talk about optimization and how that can be applied to a particular case study in Tokyo where they optimize the collection and transportation of waste. And then I'm going to go into quantum sensing. A lot of people don't know, but quantum sensors have been actually commercialized and available for over 10 years in some cases. So there's quite a few applications of quantum sensors, and we're going to talk about the energy infrastructure and transportation infrastructure use cases. And I will define what is quantum LiDAR. And then finally, we will take action, because after you listen to all of that, I'm sure you're going to want to get involved, get started, get educated about what is quantum, and so I can help you with that too. So to start off, what is the second quantum revolution? Well, wait a second. What do you mean there's a second quantum revolution? I didn't even know there was a first quantum revolution. Well, all the devices that you're currently using right now to live stream and watch this presentation, electronics, the internet, solar cells that are powering your devices, these are all examples of quantum 1.0 technology. So this technology is based on the principles of quantum physics, but they're not operating at the individual atomic level. So for example, the discovery of semiconductors, transistors, I see there's pictures here of different types of chips and resistors. These are all devices that operate based on the principles of quantum physics. Other examples of quantum 1.0 technology, broadcasting technologies and wireless communication. So this is using different portions of the electromagnetic spectrum to transmit information. So we use radio waves, microwaves, optical light, infrared light to transmit information. Also GPS. GPS is a version of quantum 1.0. Each GPS satellite actually contains multiple atomic clocks to give you ultra precise timing. So that is a quantum device. X-rays, that's using a different part of the electromagnetic spectrum to examine your body. And even the LCD screen that you're looking at right now, this is all part of the quantum 1.0 tech. So now why are these examples of 1.0 and not 2.0? It's because they're all dealing with big signals, large samples, macro states, big. The behavior of atoms in the quantum world is very different to what we see in the everyday macro world. There's other principles such as superposition, entanglement, quantum tunneling. Now, if someone just randomly walked through the wall right now, I would be very surprised. But quantum tunneling is a real thing, and we use it in devices every day. Quantum 2.0 tech, right, is referring to using these quantum properties and materials like atoms, particles of light called photons, to do a task: computing, sensing, communication, random number generation. A lot of people often will talk about quantum computers, but there's other technologies too, such as sensing and communication. And this technology, you're addressing individual atoms. So, you know, smaller than the skin cells on your skin, smaller than the molecules, smaller than that. We're actually working on the atomic level, and we're measuring these signals. Also, you can send information using particles of light called photons, and this is called quantum key distribution. And I'm going to touch on that a little bit later. But these are examples of 2.0 technologies. So if there's no questions about what quantum tech is, I will go into our demo. So has anyone ever heard of Young's double slit experiment? Excellent. Yes, from high school, exactly. This was an experiment that I was introduced to also in high school. And I thought it was just fascinating then, and I'm still fascinated by it today. And it actually illustrates some of the really weirdness of quantum. So let's step through it together. And I'll use the mouse so that everybody online can see what I'm doing as well. Okay, so whenever you're looking at these types of diagrams, you always read it like it's a sentence. So you start on the left and you go to the right. And so we're gonna start over here, and there's gonna be this light source. So in our experiment, it's not quantum yet. This is just a light source. Literally, it could be a light bulb. Then you have a screen, and it has two holes in it, two slits. And that lets just a little bit of light through, as you can see. And then for this illustration, they've made one of the paths orange and the other path blue, just so that you can watch where the light goes and why. And so as the light's traveling, you can see that it spreads out, right? Light spreads as it travels. Think of a flashlight. If I shine it to this wall very close, it's not too big. And then if I shine it way over there, it's huge. Light spreads. So as the light's traveling, it spreads, and then it starts to interfere. And so if you think of water waves crashing into each other, right? And when two waves add together, you get a very big wave. And when the two waves are perfectly out of sync, right? One's opposite of the other, like you see up here, then you would get flat line. You would get no wave, right? So that's constructive and destructive interference. So down here, you can see the waves are lined up, and then up here, they are perfectly out of sync. And so then what happens is the waves that are constructively interfering, the light waves, will make these bright lines in this interference pattern that you see on the screen. And the dark lines are from when the waves cancel, and it's destructive interference. And the demo that we've created does this with a laser. And when you take a picture of the screen in the demo in this configuration where it's just two slits and that's it, you see this interference. You see this bright, dark, bright, dark, bright, dark. And if you'd like to see more, we've got the demo set up over there. And we also have a video looping to show you, because it's kind of not dark in here, so it's hard to see the laser. So we took some video in the dark. So now what happens if we actually watch to see which way the light goes? Which slit, which path does the light take? What if we were to watch? Well, this is the weirdness in quantum. The interference pattern disappears. So those lines that we would get before are now gone. Well, wait a second. Let's take a step back. What do you mean watch? Because I'm now using my eye, right, to look at this pattern that's being formed on the screen. So aren't I an observer? Like, what is this observer over here? You're right. The definition of an observer is taking a measurement, is observing something, right? So in this scenario, there's actually two observers. There is me, physically, looking at the experiment, yes, but there's another observer, checking which way did the light go, okay? So in terms of the screen and my eye, that observer, you're measuring it, you're measuring this pattern after the light has already traveled, right? It's not happening here, it's already happened, and you're taking a picture. That light is by measuring it after it's traveled through the double slit, it doesn't change the pattern. But if I watch which way the light goes, that changes the pattern. So this observer is the one that I'm focusing on, okay? So observing which path the light takes, it does change the pattern. And that is the very interesting part about quantum. So what's going on here? When there's no observer, when this is not here, the light just travels through, it interferes, and the reason why you're getting that interference is because you don't know which path the light took. So it's in a superposition state. I know that's a scary word, but it just means you don't know which one. Is it left or is it right? So it's in a 50-50 mixture superposition state. So by observing, we know the light went through there or went through here. Just pretend in this thought experiment that you can literally watch this little slit and watch if the light goes through, okay? And if you do that, you've collapsed the superposition state. You know which way it went. So there's no interference, because that interference was due to not knowing. So once that information became available, because you have an observer watching, right? Now that information of where did my light go is available, it changes the result. This is a very, very, very fundamental concept in quantum, that observation changes the result. Now, what would happen if I would turn this light source down, right? Instead of 1 billion trillion photons a second coming off the light bulb, what if it was 1 photon a second? So I was absolutely sure I was sending 1 photon, and these photons, they're indivisible particles of light, okay? They can't split in two. They can't just suddenly clone themselves and become 2 parties or something. It's 1 photon, and it has to make a choice. That one or that one. So if I was to do that, and I don't have the observer, okay, and we send in single photons, do you think you would still get the interference fringe? Do you think you would still see interference? Because remember, That was because we didn't know which way the photon went. So if there's no observer, do you think you'll see interference? Hands up if you think yes. Hands up if you think no. Oh, see, this is where quantum gets weird. You see it. You see the same patterns with single photons, even when you're sending in the light one photon at a time. It's mind-blowing. I learned this when I was 14, and I still don't believe it. But I've seen it with my own eyes, so I know it's true. You can actually build up these interference fringes one single photon at a time. Over time, as you saturate the camera, you'll see the lines. That's incredible, right? How could it be doing that? And then if you do observe, then it goes back to being no interference, just a bright patch of light. So single photons and a whole bunch of light act the same way. So what does that mean? Well, this is again what I mean by the weirdness of quantum. So the math and the experiment tells us it's as if the photon is traveling through both slits at the same time, interfering with itself on the other side to make these fringes. But like I said, a photon is an indivisible particle of light, so that's not possible. So somehow this interference is happening, right? And then when we watch, it goes away. So it's also as if the photon is acting as if it knows whether you're looking or not. Now, I know I'm personifying a photon. No, they do not have feelings. No, they do not make choices consciously. But the math is showing us that superposition, you don't know which way it went, you get interference. You know which way it went, you know the information, no interference. That is the main concept. And why is that so fundamental? I will link it to some of the quantum tech ideas that we will discuss next. So this is the actual physical demonstration. So before, we were just using our minds, right? We were just thought experiments. Let's pretend we can watch the light. Well, now we're going to actually do it. So no observer in the path. This piece of glass here that the arrow is pointing to, this piece of glass here for the observer, what that is, it's a wave plate. It's a special piece of glass that changes the polarization of the light that travels through it. And we're sneaky. We put that special piece of glass only covering one of the slits, so one of the paths. So when we put the observer in the path, you can see on the IR card that's showing the light, you still see the two lines that are from the double slit of the light traveling through the double slit. Just like when there's no observer below that, when there's no wave plate, you still see the two lines, right? But when there's no observer, you get the interference. But when there is an observer, you don't get interference. And so what's happening here is we're using polarization to create information, basically. If the light goes through the right slit, it's going to be one polarization. If it goes through the left one, it'll be a different polarization. So because we've made the two paths distinguishable, it collapses the superposition, and now we don't have interference. So without an observer, you get interference.
Polarization?
Yes.
So by doing polarization, you know which path it is going through? That's
Yes.
why you're doing the polarization?
Yes.
But then on top of that, if you don't have an observer,
Like my eye looking at the pattern?
or a camera, yeah.
Yeah, so then we start to cross into a little bit of philosophy. You know, like if I do the experiment, did it actually get done unless I look at the data, right? No.
At the end result, that
Yes.
doesn't matter.
Right.
That's not an observer. So
Yeah.
if you don't look at the time of the experiment, you're just doing the polarization.
Yeah.
So then does it matter whether you have an observer or not?
Well, the polarization is the observer. Yeah. Yes.
Okay, so if you're using polarization to determine which slit it went through,
Yes.
doesn't that mean your slits have to be like this? So
No.
you're distinguishing one from the other by the polarization?
Yeah, but the light can still travel through the slit. It doesn't have to be a certain orientation. Yeah. Excellent questions. I know, and this is baffling, and if you want to talk more, I'm here all day, and we're right there at the demo. Oh, good. So it's a mind-blowing demo, but what's the point, right? So the main takeaway is that the act of observation or measurement affects the quantum object being the atom, the photon, the light, whatever you're measuring, right? And so what are some examples of this quantum property in quantum tech? So the security of quantum communication, for example. So there's something called quantum key distribution, QKD. Now this is the real-time generation of an encryption key. And the encryption key is being generated between two parties, Alice and Bob, A to B, right? Sometimes scientists are not so imaginative, and so we just chose Alice to Bob. And Alice is the sender, Bob is the receiver, and they're using light to generate this key. Now, if a hacker, an eavesdropper, is trying to steal information, the eavesdropper has to literally steal a photon. And as I already said, photons are indivisible. You can't just steal half a photon or a little bit of a photon. You have to steal it all. That will affect the light because the eavesdropper has to make a measurement on that photon that affects the photon. And so then Alice and Bob would be able to detect the presence of somebody tampering with their light because it affects the light, just like you just saw, right? The interference went away when observer was present. Similar things happened in this case. So an eavesdropper cannot learn your secret key without disturbing the light. And that's one of the concepts that's key to that encryption being secure. Another concept that this demo is demonstrating is a quantum computer, the fact that the quantum computer is using qubits, quantum bits, and these exist in a superposition state. Remember I mentioned superposition? So your traditional classical computer doesn't do this, right? Its bits are either a 0 or a 1. It's not in between. If it was a 0.5, that would be counted as an error and it would be discarded. Whereas a quantum computer, it stores and processes the information differently. It can exist in a superposition state of 0 and 1. And the qubit will exist in that state until it is measured. Then it will be collapsed to one value. So these are very, very fundamental concepts in quantum tech, and the observer effect is part of this concept. So are there any other questions right now about the demo? Yeah?
The photon, so when you observe it, something like, could it be like changing from particle to wave? Because they said superposition with itself, that's what the wave does. Even if you're just sending one photon, so is this part of the theory that it's something like
yes. Yes, so Young's double slit experiment talks about particle-wave duality. So the classical idea is that a wave will show you interference and that a particle will just go straight through and not have interference. That's the classical way to look at it, right?
If you look at it, then it behaves like a particle. And if you don't look at it, you cannot have an observer, then it behaves like a wave.
Yes, and so the problem with this language is that a photon is a particle of light. It is a wave packet of light. It acts like a particle and it acts like a wave. And you can get these concepts and you can create, so for example, if, so interference, you usually think of it as terms of waves, but you can get interference fringes from single photons. So particles of light can have wave-like properties. So it's not so much does the object act like a wave or a particle, it's more do I have information about which way it went? Then do I get interference or no? If I don't have path information, I know which way, I don't know, interference. And if I have the information, no interference. But I know what you mean. Usually when people explain these types of experiments, they explain interference as terms of waves and no interference in terms of particles. But that's a little bit inaccurate because of the language. Okay. So now we'll get into some use cases. So when you're solving optimization problems, you don't need to have a full-fledged, fault-tolerant quantum computer. You can use other quantum systems, and one of those systems that you can use is called a quantum annealer. So this is a picture of a D-Wave system. It's a quantum annealer. It's a superconducting circuit. So a little bit earlier when we were answering some of the other questions, I mentioned how devices that, companies that make chips and wafers, silicon wafers, they also make superconducting circuits. Because as you can see, this is just basically a computer chip, but they've made the device even smaller. Also, because it's superconducting, it has to be housed in this special cryogenic cooler. So all of this cabling and things like that, it's all to get the signals in and out of that system, and then also cool it to almost 0 degrees Kelvin. So very, very, very cold. And how these annealers work is you take one of these circuits, and you can actually program your problem. So say you have a traveling salesman problem, you have a delivery route problem, things like this. Problems that are very difficult to solve with our current computers. You can code it into this circuit and then allow it to evolve over time. And because everything in the universe wants to be at its lowest energy state, right? Think of a ball rolling down a hill. It doesn't want to stay at the top, it wants to be at the bottom. Same with this device. You code in your problem, it evolves to its lowest energy state, and that is the solution to your problem. So D-Wave uses these quantum annealers to solve various optimization problems, which are also called NP-hard problems. And these are problems that get exponentially harder to solve every time a new parameter is added. So there's so many applications. I could have filled 5 slides with all the, with the list, but I just picked 4. Balancing financial portfolios, solving transportation and logistics problems, new drug discoveries, also manufacturing. So AJ touched on some of these already, but I just wanted to highlight that again. So again, this quantum processing unit, it's going to consider all the possibilities to solving this solution, solving this problem simultaneously, and then it finds the lowest energy that's required to form those relationships, and that's your solution. So it's literally using nature to do the computation. So let's look at a case study. So D-Wave worked with Grover Knotts and Mitsubishi to combine machine learning and deep learning with a quantum annealer to try to optimize the collection and transportation of waste, and in Tokyo. So they were modeling all sorts of parameters, including the number of tenant companies and employees in each building, waste collection regulations, vehicle specifications for transport, for example, loading capacity, access and positioning of loading and unloading areas. Also the amounts, the collection routes, required labor time and collection frequency for each type of waste. The list of parameters goes on, right? And usually these are massive data sets that are fed into supercomputers that clunk along and try to come up with an optimized route for this solution. So all of that data was also combined with weather data and district event info as well, because that can change the traffic and the waste collection requirements. And they created a forecast using an AI model. So it's not just quantum, right? We always want to involve the best of the best tech. And we want to outsource the really hard problem to the quantum device, right? So AI was used to forecast the amount of type of waste that we generated over several months. And this future waste predictions actually had an accuracy of about 94%, which is very good. The AI prediction was used with quantum annealing to simulate a combination of routes and found optimized solutions that would require fewer vehicles and much shorter distances. So you can see the differences here. Even though the arrows are pointing up, these are actually differences down, right? So the current situation here, the total distance, number of trucks, 75 trucks. The working time is, a lot of minutes, almost 9,000 minutes. And once they ran the optimized quantum solution, the route distance was reduced to more than half. It's only 31 trucks now instead of 75, and reduced working time as well. So the other advantage to this is your CO2 emissions were also going to be reduced. They were reduced by 57%. So when someone asks me, how can quantum tech help climate change? That is a way. All right, so that was just a little taste of optimization. And now we're going to look at quantum sensing use cases. And there is quite a few, so this will be a little bit longer. So this is, quantum sensing is improving the sensitivity using quantum objects and properties. So when we do a measurement with a quantum sensor, you're going to have an enhanced sensitivity, better than what your current devices can do. And this is due to the quantum properties that you're going to harness, right? So maybe you're going to use entanglement. Maybe you're going to use quantum coherence. Maybe you're going to use photons and things like this. So a quantum sensor is leveraging the properties of atoms and light to improve the measurement. So here's some examples of properties that quantum sensors can detect. So gravity fields, magnetic and electric fields, single photons. So detectors that can actually detect single photons are quantum sensors. So for example, avalanche photodiodes or superconducting nanowire single photon detectors. You can do hidden object detection, and I'm going to talk about that more later. Time. You can have more precise atomic clocks. You can have individual portable GPS units that are not reliant on a satellite link. That's very important. Temperature. You can do temperature sensing even more accurately than current sensors. Also movement. There's accelerometers based on quantum sensors, and gas. So if you have volatile gas that you want to detect in your environment, and maybe it's in very minute quantities, a quantum sensor might be able to help you. These types of devices are being commercialized now and have several applications. So for example, medical imaging. So we could have a portable MRI. You could also improve image quality from a better sensor. Spectroscopy using for characterization of materials and chemicals. So spectroscopy is just the analysis, chemical analysis. Enhanced GPS, as I mentioned, and an inertial navigation systems. So this could be portable, reliable timing sources. Detection of gas leaks, remote target detection, radar systems, quantum light detection and ranging, that's LiDAR, and we're going to talk about that in a minute. There's also other industries like the mining industry would be interested in detecting magnetic fields and gravity fields. And so there's a device called nitrogen vacancy centers. And these are quantum sensors commercially available right now. There's even companies in Canada like SB Quantum that are making these devices. And you can do 3D mapping with more precise magnetic fields than you can do with conventional sensors. And finally, components for quantum computing and communication. So I mentioned how there's different platforms for a quantum computer. So there's light, there's atoms. If you have a light-based computer, you need to measure it in order to find out the answer of your calculation. That is a detector, and that would be a single photon detector. You can also connect multiple quantum telescopes to improve resolution. So there's actually astronomical applications of these quantum sensors. And in particular, since we're in Alberta, let's talk about the energy sector. So quantum sensors could be applicable for renewable energy, nuclear energy and nuclear waste management, fossil energy, geothermal energy, electricity delivery and reliability, vehicle electrification, and energy efficiency. So let's focus first on the energy infrastructure. Conventional sensors are limited in accuracy, sensitivity, resolution, how much coverage they have, their responsivity. These are all going to affect how efficient your building management is, for example. If you don't have the data, then how can you improve, right? Also, have you ever had that problem where you're sitting in your office or in a building and you have to start waving your hands in the air like you just don't care? Yeah, because your sensor is a passive infrared technology and it doesn't detect slow-moving occupants, or it struggles to detect occupants if there's obstructions. Conventional gas sensors also lack the sensitivity to detect low levels of volatile gases, which could be affecting your indoor quality. And the integration of renewable energy sources into the grid, that relies on accurate and timely data from sensors. So now we have wind, we have solar, we have water, there's so many different forms of electricity. All of these things need to be integrated into the grid, and the timing of those signals is incredibly important. And quantum sensing could help with that. timing and phase. So I know this is a big chart and it's a little scary, but we're going to step through it, and we're just going to take a look at some of the quantum sensor technologies and then their applicable use cases below. So here we've got quantum sensors for temperature and gas. That could help with your comfort monitoring inside buildings, also your air heating and cooling management. You have quantum imaging. That could help with trying to find your occupants, right? Occupancy monitoring, also the heating cooling management. Then there's solar irradiance. That could help with renewable integration. There's also quantum voltage and frequency detectors. That could help with your power quality and your grid resilience. And finally, there's devices called quantum dots, and they could assist with energy storage and energy conservation or conversion. If you'd like to know more about any of these use cases or case studies, please come talk to us after. I'm going to focus right now just on one. So for example, in the temperature and gas detection, temperature sensors that are based on single photon interferometers, interferometer meaning interference, right? So these single photon interferometers allow you to measure the temperature of inside buildings to a ridiculous degree. So for example, the sensitivity of one sensor, just one sensor, is 0.00115 degrees Celsius. That's the temperature difference that it can detect. Sensitivity is the smallest change in temperature that one sensor can detect. That's very, 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 very small. Now, take a whole bunch of sensors, have a mesh of sensors, right? Now that entire system is going to have a resolution. That resolution in this particular case, the journal article that I'm referencing here, was 0.029 degrees Celsius. Also, incredibly fine detailed resolution. And resolution is the smallest unit of change in temperature that the entire sensing system can detect. Right? So even if one sensor can be very, very, very accurate, when you combine them all together, and now you've got to combine the data, maybe there's some electronics, maybe there's some noise, maybe there's some jitter, so it might affect your resolution overall, but it's still incredibly good compared to conventional sensors. I mean, my thermostat can only do 0.5 degrees, so this is already an order of magnitude smaller. And having these more localized and precise temperature readings in buildings can really help identify these areas of inefficiencies to help improve your energy usage monitoring and even support targeted retrofitting. So what about the transportation area? Again, big scary chart, but we've got all of our quantum sensor technology up at the top and then use cases down below. So I mentioned accelerometers, and there's also strain gauges. That could be very useful for transportation infrastructure monitoring, road condition monitoring, and freight weight. And then there's magnetometers and gravimeters. Those could help with traffic flow, signal time optimization, and dynamic traffic control. Quantum radar, cameras, and LiDAR. We'll talk about this a bit more. That helps with incident detection, incident investigation, and freight vehicle platooning. There's also quantum accelerometers and gyroscopes, and they could help with cargo conditions and transportation route optimizations. And then finally, we were talking about the gas and thermometers. So that could help with detecting if you're in your cabin, if the driver comfort is okay, and outdoor and cabin gas detection. So a mouthful. There's so many different applications, and this is just quantum sensors in one little industry. And remember, there's computing, there's communication, there's random number generation. So this is just one little area of quantum tech. So let's focus on quantum LiDAR. So what is quantum LiDAR? Well, what is LiDAR? So LiDAR is similar to radar. Radar is with radio waves. LiDAR is with visible light. And basically, you're sending a pulsed signal. In this case, with classical LiDAR, it's just going to be a classical source, which means not single photons. It means a bright laser or pulse laser, something like that. And then that signal is sent towards your hidden object, right? And then that object will reflect some of the light, scatter some of the light back, and then you measure it. But in classical light, in this classical scheme, you can't tell the difference between the signal and the background. It gets smushed into one signal that you measure. And you can create a 3D map based on the time arrival difference between the sent and received light. So how far something is can tell you how long the light took to get to you, tells you how far away something is. So now, in the quantum sense of quantum LiDAR, we're going to replace the detector with a quantum sensor. So it's a single photon detector. This is going to give you a much higher resolution image compared to the conventional techniques. And these photonic quantum sensing properties, right, we're exploiting the quantum nature of light. So photons operating with light. And there's a range of applications. So in particular, we want to look at this target analysis. So now, in quantum LiDAR, the light source is a quantum source. And so it's entangled photon pairs. Entanglement just means special correlation, right? There's a special relationship between these pairs of photons, and they are entangled, in this case, correlated in time. So you can see on the image here, we have 2 spikes of data. These are the detection events that have been measured of the idler and signal photons. So that's the traditional names that people have given these particles. So when you have an entangled photon pair, one's called the idler, the other is called the signal. And because they're entangled in time, you can see on this graph that when I see a signal, I see an idler. They're always correlated. Now, the signal photons are going to be sent towards the hidden object, whereas the idler photons are actually going to be kept with the user and sent to your quantum LiDAR detector. And you'll find out why in just a second. Now, the detector is going to measure the signal photons that are coming off the hidden object as well as the background. However, what about the background? Is it correlated in time with the idler photons? No, because the background is random. And so we can use this to our advantage, and we can try to eliminate those detection events that are not correlated with our idler photons, because we know that they weren't our signal, they're just background noise. So this allows you to significantly improve your signal to noise ratio. And the distance information that you learn about the object can still be learned from the time delay observed between the signal and the idler photons. So you only pay attention to where you see this coincidence spike. And so this is extremely powerful because there's a lot of situations where you might have an obstruction in front of your hidden object, right? Like maybe it's foggy. Fog scatters normal radar, LiDAR beams. If you can cut through that fog, because even though your beam has been scattered, the signal that you do get is the signal that you want, that is a significant improvement. Okay, we did it. We got through the full lecture. We found out all about quantum sensing, and now I'm sure you're all ready to take action. Well, luckily, Cubo Consulting is here. As I said, we are consultants and trainers. So if you are interested in starting your quantum journey, please contact us. We have a quantum discovery solution program. It's roughly 4 weeks long. We go from what is quantum, we get your team up to speed on the relevant information for your organization. I'm not going to break out the textbook and start teaching you Quantum 101. It's more about targeted learning to see what is the potential of the quantum industry for you. Then once we've identified a problem that could be applicable with quantum, we can move on to the trial phase, which is roughly 3 to 6 months, where you can try a problem, identify appropriate quantum vendors. So AJ and I are very well connected in the quantum industry. We'd be happy to help you learn and be introduced to these quantum vendors and start trialing a solution. Or maybe you've already figured out what you want to do and you want to now deploy something quantum in your industry. Well, we can help train your team to be quantum ready and quantum aware so that you can deploy your own quantum solution. And finally, there's strategic foresight, developing a quantum strategy and a roadmap to plot your course for capitalizing on opportunities and minimizing the risk of this post-quantum economy. So please go to our website. There's lots of free content, blogs, videos. We have a YouTube channel, and there's lots of things to see. Thank you again for your attention. Please link with me on LinkedIn if you're interested, and check out the website. Like I said, we're friendly people. We don't bite. And I'm sure all of you have now become at least 10 points smarter on the IQ scale in quantum. So please check it out and take our quiz. It's really fun. We've come up with some, fun questions. It's not all serious. It's a little bit of humor involved. And test your knowledge with our quiz. Thank you very much. I know we already answered a lot of questions during the talk, but are there any other questions? Yes.
I have a technical question.
Oh boy.
Yeah, I have a technical question, sorry. So if you have a quantum LiDAR that is sensing a hidden object, how do you encode those entangled pairs in time so that they arrive at the same time when one photon has to travel further than the other photon?
That is an excellent question. First, the entanglement in time is going to be generated by your source. So that's already made and you're done. You're right, the path to go from your source to the detector is very short for the idler photon compared to the signal photon that's going all the way to your hidden source and then back, right? The important thing is these devices are usually set on a clock. They have some sort of timing. And so even though there's that delay, you can then overlap and find those correlated time slots, and that's how you would get the data back. So yes, there would be a big jump, but then you can overlap it and still find those correlations. Yeah, excellent question. That's more in the minutia of how we actually do it. Yes.
You mentioned, Catania, that everything in the universe wants to be at its lowest energy state. How does frequency and vibration also affect that energy?
Excellent question. So right now, we are in the era of noisy qubits. That's what we call it, right? So a quantum computer, we use qubits, right? And the noise of the environment disturbs the system. So exactly what you're saying, right? So in the terms of like a superconducting circuit, for example, we want it to be super, super cold, lowest energy state. But then the heat of the room could increase its vibration, could warm it up. And then that would actually destroy the quantumness, and it would turn it from a quantum thing to a classical thing. So when we're dealing with vibrations and noise and frequencies and things like this and heat, we want to minimize it as much as possible because it will transition your quantum state to a classical state. Excellent question. Well, one more.
Thanks. I have another technical question. So how far in free space can you do a quantum LiDAR like that?
So with quantum LiDAR, you would need line of sight, basically. And so in terms of free space, as long as you've got line of sight and you can still pick up your signal, it's strong enough, then it should work. Yeah. So the curvature of the Earth? No, because the signal, yeah. So you have to have line of sight, but then it has to be close enough that you can still measure the signal. Because as I mentioned with the flashlight, light spreads, right? So if I shine a flashlight to this wall, it's gonna be maybe a foot big. And then if I shine it way over there, now it's like 3 feet big, right? So the light's gonna spread. So even if you're sending a signal from the Earth to the moon, it'll eventually get there. But when it finally gets there, it's gonna be very, very weak because it's spread so big. Like when we were doing the satellite experiments with the KeySat, the quantum encryption and science satellite, we're going to send light from the ground that's only 8 inches in diameter. By the time it gets to the satellite, it's going to be several meters wide. Yeah. And that's the best that we can do. We're making our telescope to make it as what's called collimated, so the light is all parallel, so it doesn't spread as much as, you minimize the spread as much as possible, but it still spreads. So with the LiDAR, that's one of the limiting factors.
So how far is free space QKD possible? Is it still
The longest demonstrations in free space QKD that I'm aware of is like 50 to 100 kilometers, maybe. I would need to look it up. But again, that's the problem. Like after like 20, 30 kilometers, your atmosphere, when you're dealing with these experiments on the Earth, you have to send the light through the air. The air messes up your light. It absorbs some of the light, it scatters some of the light. So everything that gets lost destroys your signal. And so as long as you can still pick up your signal, then it's possible. Yeah. Good questions.
Oh, Anne. Hi. So you were mentioning a bit about transportation and everything like that, and it's all kind of land-based, but there's a lot of innovation happening in drone technology and airspace management. So I'm assuming there's a lot of interest in like quantum computing in relation to those areas. Have you heard a lot about how that's being leveraged?
Yes, definitely. There's a lot of talk for drones because these quantum devices are nice and light. They're small, they're compact. Usually they use less power to operate, things like this. It depends on which platform and which device, right? This isn't universal. But I'm saying there are devices that are being designed to be space ready and drone ready. And so I'm aware of drone demonstrations using quantum key distribution where they demonstrated quantum communication doing it. I'm not sure about optimization and things like that, but definitely for sensing. So you know when we currently have drones flying around the city doing all these LiDAR and measurements of the roads and things like that, that has been done, I believe, by other cities, by at least trials, where they put quantum sensors in there. So love to talk more about that. And wastewater management, wastewater and flood modeling. But that's not really drones. Yeah, it could help. It could help. But I know with Calgary, we're very interested in when the river might possibly flood again. And so that's a serious problem that's been studied by other institutions as well. And I'm aware of a use case in Vietnam where they modeled their floodplain and they were able to come up with optimized ways to find, okay, this is where it's safe, this is where it's not, this is the predictions for the future.
Cool. So we talked about the surf wave yesterday, I think it was. But so there's a surf wave. We actually have a wave that was downtown, and it was caused after the floods. And then what happens is that it caused a buildup of sand, and the silt is built into it, and the wave's gone. But there's a real push to mitigate that by putting in a man-made surf wave, and it would have a bladder that blows up, and then it would have a adjustable surf wave. It's really cool. But in Ottawa, they've built a room twice this size, and they've actually modeled the 10th Street Bridge and the river and everything there, and they're using quantum computing to look at all the different models of what's the best way to mitigate the floodplain and the silt buildup. And it turns out a surf wave, which would be super fun, looks to be the most effective way to reduce silt. But they're using those high compute modeling that can happen in a controlled environment. Okay. Thank you very much. So let's take a 10-minute break, and then we'll reconvene at like 5:02.
Hi, everyone. Thanks for coming for one of the last sessions. This is the second last session today for Quantum Discovery Day. And we have Megan Lee, who's going to be talking about Quantum City and its program. And so I'm going to hand over the mic to her. Thank you for coming, Megan.
Of course. Thank you. Oh, thank you. Thank you, David. Yeah. Thank you, David. Okay. Hi. My name is Megan. I'm from Quantum City. I know many of you have heard about quantum science and quantum technology throughout the day, and you may be wondering, okay, so I'm interested, now what? Like, how do I get my quantum journey started? So I want to talk about our initiative and then the programs we have available for you as a resource. I'm not a quantum scientist. I'm a scientist, but not quantum scientist, so this is not going to be a real technical talk. So, all right. So we started about 2 years ago as a strategic initiative between University of Calgary and the government of Alberta, and our first anchor industry partner emphasis. And our vision is to become a global quantum solutions hub, where quantum tech becomes quantum solutions. So when we started about 2 years ago, we did sort of an environment scan. And so we're one of the 4 quantum hubs in Canada, for example, and there are quantum hubs around the world. But we really felt that gap in the ecosystems was on the quantum adoption side. So many hubs focus on pushing the IP out of the lab into startups, hoping some of them will turn into unicorn. I'm sure some of them will. But if you ask a startup, what's the biggest worry? It's the first customer, the revenue generating customer. Grant is great, but that's not revenue. They're looking for their first customer. So what we're hoping to do is, create the customer base. So essentially help the potential adopters and users of quantum solutions and create that market pool. So under this vision, our mission now is to capture the benefit of quantum tech by creating adoption pathways. Quantum City is here now building an ecosystem for quantum science technology in Alberta, bringing together researchers and developers and industry and adopters of quantum tech and science services. So we have 3 strategic pillars of activities. First one is establishing and operating enabling infrastructure in quantum. Second, we're creating a pipeline for talent and experts. And third, we're narrowing the gap between quantum tech and quantum solutions to support the development of a vibrant quantum economy here in Alberta. So for the infrastructure side, Q-Hub and Q-Lab are our 2 major initiatives we have going on right now. So Q-Hub is a collision space for quantum researchers, users, and creators. And programs will be available within Q-Hub, which include startup incubation, knowledge center, and a membership program, amongst many others. And Q-Lab is in current development, and it will be located within the Q-Hub. So Q-Hub will host clean room spaces, advanced fabrication tools, and characterization services to serve both research and industry. So these buildings are actually in University Innovation Quarters, so just north of the U of C main campus. And Q-Hub will actually open very soon. So we're looking at February or March of 2025. And it's about 17,000 square foot collision space that will support, of course, essential Quantum City activities with offices and meeting rooms and event spaces, hot desks and labs and workstations. And the architectural design considerations were, of course, for promoting the interactions between quantum creators and quantum users, such as collision spaces, Blackboard integration everywhere. Apparently physicists don't work on a whiteboard, they insist on Blackboard. So Blackboard everywhere and a cafe bistro. And right next to the Q-Hub will be Q-Lab North. So we have Q-Lab North and South, but North is the main location. So this is a clean room facility with 3,800 square foot of space, and this will be the cleanest semiconductor space in Alberta, essentially. So it's an open user facility to promote industry engagement, basic science and R&D, and prototype development, and it'll house all these state-of-the-art tools that I mentioned here for quantum device makers. Okay, so now moving on to the industry engagement side. So, we heard quite often from the industry, okay, Megan, you sold me. I'm interested in quantum, but how do I get started? I have no in-house capability. How do I even get started? So based on that demand, we created this program, Scientist Residence Program. So many of you might have heard from our first SIR in quantum algorithm, Dr. Adam Benny-Watts, sitting right here in a beautiful orange fall color here. So I would say, think of these SIR as the world-class researchers that are available as your guide in your quantum adoption journey. So they'll bridge that gap between academia and industry. So depending on whether you're a quantum creator or user, the mode of interaction will be a little different. So for the quantum creator, the SIRs will be available for secondment, so that could work with you within your company for a short-term period of time. But if you're a quantum solution adopter, that can be your guide in your quantum adoption journey, whether you're just looking at, hey, I know nothing about quantum, can we just do a sort of a educational discovery workshop, to an actual, full-on engagement, that sort of an R&D project that involves, of course, SIR, but faculty, researchers from University of Calgary or kind of from around the world where we have connections with, and that could, engage interns that are, studying on campus here, or your current workforce for reskilling and upskilling opportunities. So Quantum City Challenge was probably our most public event or initiative that we did in industry engagement side. So it was a global quantum tech competition that started in 2023 and ended in 2024. And we essentially challenged the experts and enthusiasts from around the world to solve Alberta energy industry problems using quantum knowledge. So it was made possible by Quantum City, AWS, and the government of Alberta, of course, and the University of Calgary, our two biggest supporters. And the competition focused on 3 problem statements from 2 companies that you know of, ACCO and Canadian Natural. So ACCO gave us a problem statement on EV charging optimization on a hypothetical city, and Canadian Natural gave us 2 use case problem statements on tailings treatment and bitumen viscosity for transportation. It was interesting enough, the motivation for participating in the challenge for the 2 companies were different. For ACCO, it was the journey. They wanted to sort of experience the experimentation of quantum. They wanted to even how to put a problem into a quantum relevant quantum problem statement, and also go through the process with us, with our SIR, and even learn how to assess a potential quantum solution. Whereas for Canadian Natural, their motivation was solution. These are the problems they have been trying to solve for a long time, and it was very costly. So for their opponents, like, I'll try anything. If this can solve, even if it lead to 1% improvement over the classical solution, I'll be interested. Let's try it out. So the winners were unveiled at our annual summit, QConnect, in 2023. And they were so Angel Q, which is a startup in Singapore, and Accenture, which is a global consultancy firm. So after the winners were announced, we're hoping to have some follow-on projects, but nothing formalized yet. Another initiative that we launched recently is the membership program. So our membership program offers access to, or priority access to resources and insights and expertise to help you stay at the forefront of quantum advancements. So number 1, priority access to our events that we'll be hosting, especially at Q Hub, including Q Connect 2025, which I'll talk about later. Number 2, priority access to road mapping services. So essentially, this is a collaboration with our SIR. So we have SIR, of course, in quantum algorithm, Adam here, but we also have SIR in quantum sensing, and also quantum safe communications. So these services are just to work with our SIR and quantum experts that we have access to design customized quantum integration strategies specific to your organization. And number 3, member will have priority access to our solutions lab, which I'll talk about in the next slide, and access to our community reports. So stay informed with newest trends and the news in quantum. All right, and we have wonderful advisory committee to kind of, guide us along the way, just to make sure we are creating a membership program that provide value to the industry and the solution adapters that we are hoping to serve. So David, thank you very much for agreeing to be our advisor. And the Solutions Lab, so our Quantum City Solutions Lab is the motivation is to, number 1, drive innovation, number 2, empower startups, and number 3, to collaborate with industry. So our goal is to accelerate the development of quantum solutions by connecting the industry with innovators to solve real-world challenges. So it bridges cutting-edge research and practical applications, again, driving innovation and growth. And Solutions Lab is supported by Alberta Innovates. So that you might think, okay, so you're working with industry, you want to solve the problem, but where is the innovation coming from? If you're creating all these demand, essentially, where's the supply coming from? And of course, the innovation and IP comes from the university many times, but often really innovation comes from startups. And quantum is so new, we can't just focus on Alberta only or Canadian only startup. We wanted to have access to startups from around the world. So in fact, I think stats is kind of sort of vary depending on where you read, but I think 70% of the startups, quantum startups, were created in the last 3 years. and there are about 350 startups. So it's a really new sector, and quantum is not developed just in our backyard. It's really being developed everywhere. So we wanted to sort of have a really great deal flow from all around the world. So we partner with Kai Ventures, which is Basel-based quantum-specific venture fund. And they've opened up their Canadian office, or North American office in Calgary. So they've chosen us, their first outside of Switzerland, outside of Europe office. And they'll be running their accelerator program in March of next year, housed in our collision space Q Hub. So David, in the back here, he's the head of the accelerator. Yeah, that David. He's the head of the accelerator. So we'll be seeing 5 to 10 startups from around the world going through the accelerator program here in Calgary. And it's the final slide on Q Connect. So this is our annual event. Really, we started this event because we were getting questions from industry. Okay, I don't want to go to a scientific conference because I'm not a scientist, but I want to know about the use cases, meet potential users or startups, or just even find out what others are doing. And we couldn't really find an event that we liked enough to recommend. And naively, sure, I can have an event. How hard could it be? Don't do it. But it's been a great experience. It's been, we've been getting overwhelmingly positive feedback. So this was our second year hosting, and of course we'll have Q Connect 2025 next year in November. So we typically see about 300 attendees from really around the world. This year we had more international attendees than last year. We had one from Japan, we had Korea delegation, that we had European delegation. So it's becoming really international. And so this year's our major panels were quantum and human health, quantum and sustainable cities, and quantum and modern energy. So I highly recommend that you come check us out next year in November, Q Connect 2025, which is the year of quantum, by the way. So that's it. If you have any questions, I'll be happy to answer. But I strongly recommend that you follow us on LinkedIn. That's where we put all our events and our news. So happy to answer any questions from here. Thank you. Done such a great job. There's no question.
You can keep this one. I'll see this one. Are there any questions? I have a question.
Yes.
So the city of Calgary or other municipalities as well are probably a source of use cases, all different types of optimization use cases.
Absolutely.
How would we engage with you to unravel these use cases and submit them as potential ways for your experts to look at?
Very good question. So I would say first point of contact should be either Ryan, our industry engagement manager, or our scientist residence, Adam. And so I can go back to the program we talked about, the solutions lab or the use case development. So that's sort of a program that I can think of ways to engage folks like City of Calgary with, like beautiful use cases of holders here. So yeah, so I would say talking to these two will be the best way to do it. I think for Solutions Lab, we are thinking about having an online portal so you can submit a question. I don't know if that's up yet, no, but soon it will be up on our website where you can submit a potential use cases that you want to explore. Then yeah, we'll be happy to work with you.
Okay, thank you.
Thank you.
Questions?
Oh, okay.
Give me a second, Ann.
Okay. I think mine is somewhat like Dave's, but a little bit different. So you were talking about your scientists in residence and everything like that. So if a person has an idea and they come to you and they're like, I have an idea, but I think that it's going to need some sort of quantum capabilities. Is that how it starts? Like, is that the workflow that a person would go through? They just come to you, say this, and then they just get paired, or what does that process look like?
Yeah, so actually often when we even hear about our use cases, I think Adam can correct me if I'm wrong, many of the cases they're like, I don't even know if it's quantum relevant. and we'll be able to help you whether if it's quantum relevant or not, and if it is sort of just like what we did with ACCO and CNRL. We took their challenges and turned it into a quantum relevant problem statement, which is an extremely difficult thing to do, and not a lot of experts can do that actually in the world. So that's something we're building internally so we can help the industry. But yeah, definitely we get the question a lot. I'm like, I've got this problem, maybe it's quantum, maybe not. So we're here to help you. Yeah.
So that first stage would be like a discovery that's all about like problem definition.
Yeah.
And then after that, you
That's
might,
right.
okay,
Yeah.
that's awesome. Thank you.
Did you want to add something, Adam? No? Okay. Oh, question here?
Oh. Hey, Sandra. Here. I'll give you this.
That was a very enlightening
Ooh,
presentation.
okay, thank you.
Thank you. You mentioned ATCO and CNRL. Now, were those problem statements, were they able to be solved? And were they also able to be put into application?
Very good question. Adam, you gonna take this one?
Sure. We'll probably say the same thing. I'll grab it. Okay, you know, in a word, no. But that's not to be pessimistic. I mean, that's not me being negative. So, okay, were they solved? Yes. From earlier at lunch, you know, the state of quantum computers and the state of quantum technology is such that the sort of problems that you can solve right now on quantum computers, it's very hard to get a problem that's big enough that it competes with like utility scale solutions that are already out there. So what we saw in the solutions that we got was not we're doing better than the best classical solution right now using the best classical technology. We saw an indication that something interesting is happening. That means that as quantum computers get better, this is an interesting question to revisit, an interesting problem to revisit. So there were positive results, but they weren't let's deploy this today. They were let's wait and see, let's keep up to date on quantum technology. Let's revisit it in a year and see what happens. Yeah.
So then now, are you going back to a classical solution?
Yeah, so I mean, I'll talk about the ATCO one just because it's maybe a little easier to describe. So that was a question about how you scheduling charging for electric cars in a hypothetical future city. So, you know, already the problem was hypothetical. If you had to solve that problem right now, your best bet would still be to use a classical computer and state-of-the-art classical techniques. Now, in a couple of years, as quantum technology gets better, is it going to start outperforming those state-of-the-art classical solutions? Maybe. And we sort of, the result of the ATCO challenge was we have an idea of the algorithm we would want to run and want to try in another year or in another 2 years. So, yes, and this is not, I should say, unique to this challenge. This is quite often the state of quantum these days. Is you know, you see promise and you see potential, but in a horse race against the very best classical technique, you're maybe not beating it yet.
So essentially, from what I'm understanding, is that the problem needed to be more complex.
Yeah, and the hardware needed to be better. So there's a limitation just in terms of the quality of the quantum computers that were built and that we had access to. And already we have better quantum computers, you know, just better machines than what state-of-the-art solutions could use for this challenge. I mean, this challenge was a year ago, and that's already pretty out of date in terms of technology. So I would be interested in rerunning exactly the same solution on a state-of-the-art quantum machine today and seeing how it does. But yeah, going into the challenge, looking at sort of the quantum computers that teams were getting access to, and keeping in mind that, you know, using the very cutting edge is very expensive, and for a challenge like this, you have to stay a step back from the cutting edge, just because you want it to be global. You want lots of people to be able to try it. You know, the target was never to beat state-of-the-art classical, but it was to show an idea that looks like it has promise. And that's sort of what we got out of that challenge, if that makes sense.
I'll just add one thing though. So, you know, did this challenge solution impact their share price? No. But I think for industry that we work with currently, they also see it as an sort of a attraction of a new workforce tool. So number one, it will take time to train the workforce or even to figure out a problem statement that is quantum relevant or they want to try it out. It's kind of like a Y2K, right? It's not gonna be done overnight. It takes time to find the right use case, train your workforce, and essentially they also started as a way to engage a current workforce or attract new engineers to the company. So that's another, maybe not primary motivation for doing it, but that was a secondary motivation doing it.
Okay, any other question?
Yes.
Yeah, go ahead.
A follow-up question.
Can you provide an example where quantum computing was able to provide a solution to a very complex problem, a use case for that?
Like the chemistry problem, or?
Or the last mile.
Okay. Yeah, go ahead.
Wasn't there one on protein folding?
Yeah, okay, yeah. Sorry. Yes. Yeah, okay, no, it's a great question.
Great, I call a friend and he just shows up.
I feel bad, I'm taking over your presentation. No, okay, it's a great question. It's a great question, and the answer is more nuanced than I would like it to be. There are cases where quantum computers are being used right now at the industry scale. The Port of San Francisco, the San Francisco Port Authority uses a quantum computer to schedule loading and unloading. Last mile food delivery, I think with Pattison Food Group is another one. Both of these use a D-Wave quantum computer. And so these are examples where quantum computer is seeing commercial use. Now, when you ask me this question as a scientist, there's another question, which is this quantum computer really doing better than the very best classical solution you could have come up with for this problem? Now, that's not the metric you need to beat, to see it used in industry. If it's seeing commercial use, that's great. Would I point to that as an example where a quantum computer we know is outperforming the very best classical solution possible? I'd be hesitant to point to that. And I think, we talk sort of about the killer app for a quantum computer, the one that's obviously outperforming anything you can do classically. And we haven't seen that yet. But that's a very high bar, right? It's like saying, not only bring a solution to market, prove that it's better than absolutely every solution out there. That is the standard that we haven't hit yet, but we think quantum computers will hit one day. But we're seeing these commercial applications. There's Megan mentioned protein folding, and we've got ideas a lot to do with sort of simulating chemistry or simulating quantum physics, simulating nature, where we think quantum computers will be able to do things that no classical computer can do, but that requires the hardware to be better. And we just haven't hit that level of hardware yet. So nuanced answer, but hopefully that, yeah.
So what is it about the hardware that needs to be better?
Yeah, I love this question. Yeah. In a word, in 2 words, noise and size. So size refers to how big, literally how many ones and zeros you can squish on your machine. How many you put in, how many you get out. The computers we have right now are limited in size. So, just the type of problems you can solve just aren't that big, like most commercial scale problems need a lot of ones and zeros because you're thinking about a very large system. D-Wave is actually a machine that's fairly large, but most of our quantum computers are fairly limited in size. The other sort of subtler issue is one of noise. So inside your quantum computer, you have a bunch of operations that are going on. Every time noise means that you try and implement an operation and you get something a little different. So You try and add two numbers together and you get it right 90% of the time, but 10% of the time you get the wrong answer. Now, the problem with this noise is that as your computation gets longer and more complex, these errors accumulate. And so when you have noise, you're limited in the sort of computations you can do, because if a computation is too long, you see more and more errors and it just ruins the output. So lots of the potential killer apps for quantum computing are very subtle, are very delicate. And so even one error along this pipeline will completely kill your result. We have other apps that are more robust, other ideas that are more robust. Those are the ones that we're trying right now and using right now. But these sort of, the more delicate ideas, we just can't run right now on a quantum computer because of errors, because of noise.
Thank you, Adam.
Oh, I'll talk to Cubo and see if they can add it to the quiz. Okay. Don't let me stand back up again.
I have another question. Okay, so let's say we come to you guys with a number of different challenges. What's your capacity in terms of intake? How many, or what would you expect you'll be able to take in for challenges or problems to solve? And what's your capacity in terms of intellectual capacity? How many experts do you have that you can throw at a problem?
That's a very complicated question. I would say simple way to answer is that, so we're not the one who's often creating the solution, right? So like all the activity will be guided by our SIR, our scientific director, but we would want to engage essentially the owners of the data from the challenge sponsor, but also we will want to bring in trainees as interns into the project. So it's not just like, we only do one project at a time, because essentially we can create a pods of, working group depending on how many challenges we have going on. And then the question is like, what's the maximum number of challenges we can take on at the same time? Good question. I don't think we've stress tested that yet. I would say we have capacity, as in funding. We have capacity to do like 6 to 7 challenges at the moment. That's funded by Alberta Innovates. But yeah, so I would say, maybe 3 is a good number to start with, but to be honest with you, I don't think we've stress tested that yet.
Okay, good. Thanks. Any other questions? Okay, well, thank you very much, Megan. That was excellent. And so next we're going to have a presentation. If you want to know how city service and quantum can be applied to a city service, we have the Fantastic Five coming up, and they won the quantum hackathon that Kai Ventures, David back there, put on a few weeks ago, and they used the snowplow optimization problem to as their challenge. So just going to give us a couple of minutes to set up here, and then we'll begin. Okay, here you go. Here's the Fantastic Five, everyone.
Good afternoon and welcome, everybody. We are the Fantastic Five. My name's Kevin. And back on October 6th, our team was judged best overall at the GenQ Quantum Computing Hackathon. And we'd like to give our presentation to you here because we think it'll be a tremendous benefit to the city of Calgary. Let's begin with a story. Imagine John. He's had a really hard day, and all he wants to do is go home. But oh no, there's a huge dump of snow. That means that there's slow traffic, lots of accidents, and it's 75% worse because of delayed snowplows. But what's worse is there's no way he's going to be on time to pick up his child from the daycare. This makes John so angry. So what can he do? Well, he can call 311 and complain. Do you want to be the one to take his call? Me not. But during the hackathon, it turns out that John isn't all that an imaginary person. We interviewed 3 people. Alice here says that she's given up calling 311. And Tom, who's a doctor, is always worried about getting locked in because he has to get to a hospital where he's urgently needed. And Emma here knows that there is a snow clearing map, but it's not really good for driving. Turns out that these people aren't alone. According to the latest satisfaction survey data back in the spring, 98% of people think that snow clearing is important, but only 70% say that the city is doing a good job. Only one other city service has fared worse with these numbers. That's affordable housing. This is a big red flag. Now, to be fair, this is not an easy problem to solve. You have to consider such things as the width of the roads, how much traffic there is on the roads, the fact that snowplows have difficulty making U-turns. Some roads are a higher priority than other roads. Some roads are closed to construction or for other reasons. Some roads are one way. Snowplows have difficulty getting uphill sometime. And we also have to keep track that the snow is constantly falling. But what makes this even more complex is that we don't have to solve for just one snowplow. We typically have to solve for about 58. All of that means that this is a super complicated problem. Now, when the GenQ Quantum Computing Hackathon was announced, I saw this as an opportunity to help my fellow citizens. I too have been stuck in the snow. For me, this was personal. Japnet, do you think our team's up to it?
Definitely, Kevin, because we have a mix of software engineers, people who are good at quantum, as well as a business thinker who makes sure that we come up with a solution that is not too theoretical. And after 2 sleepless nights, juggling work meetings while working on the hackathon, submitting the solution after literally 500 tries because the platform kept failing, singing on the rooftop, and making 50+ Canvas slides, it was all worth it because we won the entire hackathon. We won the snowblowing challenge. A lot of bragging rights for us that weekend, and it was my first hackathon win as a software engineer, so very proud moment for me as well. And this is the solution we came up with in just 48 hours. Our vision was to disrupt the route planning mechanism currently employed to not only help the city, but also the citizen as well as the snowplow driver. And our solution is a hybrid solution called Street Guardian, which transforms the Calgary's road conditions map into a powerful quantum-powered live Google Maps application. And yes, we made a small beta during the hackathon, and I have a demo that I want to show to you guys. So we have a use case for the car driver and the snowplow driver. So imagine you want to get to work. Now you can clearly see which roads have been plowed and which haven't, so you can safely reach your workplace. But let's say there's a shortcut that you want to take and that hasn't been plowed. You can quickly report it. All of this feeds into our central system, which takes into account other factors like traffic, citizen reports, maybe congestion, to automatically reroute the snowplow. So this was our great vision, and this is what it looks on the city's end. Now the city would be able to take note of the construction areas, the congestions, be able to track each snowplow, be able to call the driver, reroute them, set priority zones, as well as, let's say an emergency vehicle is stuck in the snow, we want to reroute for that, calculate the reroute possible for that. Let's say there's certain lanes that are being reported by the citizen more often, or weather conditions that have changed and it's snowing again. So many different variables that we need to keep track of. I know it's very confusing, and classically it's very hard to solve. So Jamal, how are we gonna solve for so many variables at once?
Probably we are going to use some sort of magic. When we are talking about superposition and entanglement, it might sound like magic, but there's a fine line between quantum science and being a magician. So let's go into the details of the quantum principles. In classical situation, we have bits, which are either 0 or 1. But in the quantum situation, we have 0 and 1 at the same time. That calls superposition. Let's do a thought experiment. let's have a cat and put it in a box with a poison. If you don't look into the box, the cat could be at the same time dead and alive. Dead means 0 and alive means 1, which is the meaning of superposition. So let's look at the entanglement, the other superpower of quantum. When we are bringing two qubits together and interconnecting them, those two create one object, which at the end of the day, they have 4 possible outcomes. If you want to do another thought experiment, we could think of the entanglement as 2 qubits are interconnected together and playing seesaw, which means affecting one of them could affect the other one immediately. So those are the superpower of the quantum. And the way that we are going to use them is that if we compare classical computer and the quantum computer, in the classical situation, we have to try each of the possible answers one by one. But in the quantum situation, we could use superposition and entanglement to try all of the possible situations and come up with the best one. If you want to think mathematically, what happens is that in the classical situation, it is so hard to not fall into the trap of local minimum, which like what happens for the Red Bull. And for the quantum path, which we are using tunneling, there is very possible that we find the global minima by finding a minimum possible energy in the energy landscape. But how we are going to use all of these to solve the real world problem? Because quantum is not enough. We have to use classical computer as well. We could perceive the quantum processing unit something like GPU that has to have CPU alongside. So the classical computer could optimize the parameters, and quantum processing unit can handle the hard problem, which sometimes is doing the optimization part. During the hackathon, we used different optimizers and different ansatz to find the best runtime possible. So we could deal with the realistic configuration of the city. We used IBM quantum computer, and it turns out, based on our simulation, if we are able to simulate for 12 nodes, we could surpass the classical solutions and show the supremacy. But here's the thing. Our quantum machines are noisy. Thanks to Adan, I have the easy way to explain why does that the case. Because it's not about just having more qubits. It's about being able to mitigate those errors. So as you can see, computing volume would be increased if you have more qubits and less error rate. So during the hackathon, we came up with this idea to use cat qubits because we could mitigate the error significantly by finding the sweet spot of using the number of photons in our simulation. So what does that mean is, even though we have like error prone machines right now, we could do something meaningful with them. But that's not the only case, because as we can see, the graph shows that there are a lot of new players coming to the game, and the number of qubits are rising. And there is the possibility of using these quantum computers, even though they are noisy, in near future. And the way that we are proposing is using D-Wave plus NVIDIA. It turns out that using hyper-performing computers plus quantum processing units from D-Wave, it's the way to go, because the way that they benchmarked, it turns out if you want to communicate between hyper-performance computing and what's going on, and the QPU, it takes less than 10 seconds to transfer the data between those two processing units, the classical and the quantum. And based on the latest research papers, like comparing the classical solutions and the quantum solutions and the hybrid solution, it turns out the hybrid is the best answer. It can find the solutions much faster compared to the classical approach sometimes, and sometimes it's comparable. This is with D-Wave machine, with the previous topology. But with the next generation of topology, as Adam mentioned, we have the ability to surpass those solutions that we found. Here I'm going to explain what's going on. So we have the orange one. That is the new topology of the D-Wave hardware. And it turns out, in terms of average runtime, that is much faster than the previous topology. And just look at this graph here. If you could do something with the previous topology and surpass or be comparable to the classical situation, what would we can do with the new topology of D-Wave? And that's going to be released very soon, because D-Wave shown this topology in 2021. So that's why we could use quantum hybrid solution, because we can do fast optimization in less time and less fuel consumption, which is aligned with the city's goals. So classical computers brought us up until here, and we are so grateful because of that. But here's the thing. There is a plateau of the growth of the classical machines. And we have the opportunity right now, today, to embark on the journey of using hybrid classical and quantum solution, so we are ready for the future of quantum era.
The importance to invest right now is because we know quantum is going to be the future. Maybe not tomorrow, maybe not the day after, but it's going to be here. And just to understand how we can use an approach to solve with classical and quantum, let's slice the elephant. I do want to make a declaration that no animals were harmed during the making of this presentation, because I think we have seen a cat, a rat, and an elephant by now. But what we are proposing is a divide and conquer approach. We do not need to solve for the entire city of Calgary right now. We can solve for subsections of that map. And we were able to solve for a very small 4-node graph in just 48 hours, which is a small subsection of the city of Calgary. And what we have seen in recent research is this divide and conquer approach actually being used. So for an optimization problem, we will decompose it into smaller problems, solve those smaller problems separately, and then combine the solution. The really cool part about quantum is that if we decompose the graph in a very smart way, we can actually change the initial Hamiltonian in such a way that quantum is able to even perform better on these smaller problems. Classically, this cannot be done because an NP-hard problem will remain an NP-hard problem even on a smaller graph. So this is why we're very excited about this possibility of using a divide and conquer approach and be able to solve for the entire city in the next few years. And to see how we're going to get there, we have a roadmap for all of you. If we start research right now, we can collaborate with key stakeholders of the city to get some insights and work with them so that we can come with a quantum-ready data model in the next 3 months, which is going to be our first prototype, while as well developing the application for the planning as well as the snowplow driver app. Now, this would mean that by next winter, we would be ready for a small pilot test in downtown Calgary, which would be basically daily optimization for the routes, maybe not real time, but also enabling real-time tracking of the plows so that citizens can know which roads have been plowed and such technologies. We'll be able to use the feedback gathered from this initial pilot test to be able to integrate and optimize our application through agile development. And the cool part is that we don't need to wait for the next winter to try again. We can try with Calgary street sweeping because it's the same problem, or expand into different industries like garbage, deliveries, agriculture. So if we are able to invest in the solution and solve this problem, we're able to solve a lot more optimization problems as long as we can translate them to our solution. And what we've been trying to do for the past 20 minutes is try to convince you that the quantum future is here. But if we weren't successful, maybe someone from the city can convince you. So we have a quote from David. And he thinks that our world is a big quantum machine. So what will happen if we actually start rebuilding applications and use cases with the power of quantum? I would like to take this opportunity to thank the City of Calgary for taking part at the hackathon and enabling us to work on this real world use case, as well as having the city representatives be so kind and give us feedback and this opportunity to present to all of you. I would just like everybody here to take 1 second. We were 5 people from 3 different countries. We met on the day of the hackathon, and in 48 hours, we came up with a solution. With the right resources, with the right time, and putting all the efforts that we can into this, just imagine what all of us can do together. And City of Calgary, let us start your quantum journey. Thank you.
We can take questions now. Thank you. I appreciate it.
It's super inspiring to see brilliant minds put to use in such a short time. You came up with a solution. You know, we've been talking all day about how long it could take to come up with a quantum solution, and yeah, you guys demonstrated that. You know, you can do it very quickly, and that was very inspiring.
You were looking for a killer app?
Do you have any questions from the audience? Thanks, Katania.
Well, congratulations. I was witness to your hackathon, championship, so well done.
Thank you.
You said 4 nodes to do that little section. Do you have an estimation of how many nodes to do a larger section of Calgary, or even all of Calgary?
So based on D-Wave's papers that is out there, they have tried to do for 35 nodes, and they are like finding the solution immediately. That is for optimizing the driver optimization problem, which is something relevant to this that we are doing, but we have to tailor that solution to our problem as well. And they are just using their like hardware. They are not using NVIDIA plus D-Wave type of thing. And those things that they are doing, like a little bit outdated with the newest algorithms that we found in the papers that also are using D-Wave solution, we could do much better than that. And I want to highlight something very interesting about this to hammer this home. Because the problem with the classical computer is that we are using gradient descent, right? But the good thing about D-Wave approach and quantum annealing in general is that the runtime is in the order of 1 over g squared. And g is the minimum gap between ground state and the first excited state. And the way that quantum annealing works is that you're finding the initial Hamiltonian. So that's much easier. And then by evolving the system, you're finding the final Hamiltonian, which gives you the optimized value. So here's the thing. That's the idea that we want to pursue. If you find the initial Hamiltonian by decomposing these graphs into smaller chunks, such a way that we find those initial Hamiltonians that are much easier to solve and much faster, we can do much better than classical situation. And to top it off, we can do AI to reinforce that finding the best Hamiltonian, the initial Hamiltonian. So we can come up with solution much faster. So this is the idea that I came up with like yesterday when I was talking with somebody else. So this is what we want to pursue. Sure.
Sandra.
So you mentioned that you had implemented a hybrid solution between classical and quantum. When you implemented the quantum component, how long did that take? What was the time frame?
So great question, because so initially we were using IBM because that was a restriction from the hackathon. From the beginning, I just wanted to use D-Wave, but I don't know why they try to restrict us to use IBM. So it turns out if you really want to solve for longer nodes, like a bigger chunk of the city, it takes like an hour, like you doing like 6 node. That's very hard to do with the IBM right now. And the problem is that, so the reason why I'm insisting on D-Wave is that this is inherently D-Wave quantum annealing in general. It's not about D-Wave. But the company that does the quantum annealing and commercially it's available is D-Wave, right? So those quantum annealings are inherently good for solving the optimization problems, especially QUBO, quadratic unconstrained binary optimization. The reason why is because they are very natural to solve the Ising model. And the Ising model is like having those superconducting qubits in D-Wave. And it's very easy to transfer your mathematical problem into the quantum simulation and transfer those QUBO problems, that is finding the cost function, the minimum cost function, and transferring to the quantum simulation so you can find the, like in the landscape of the energy, find the minimum energy. That is what we're trying to do in classical situation, which is hard by doing gradient descent. But it's much easier when I was talking about like quantum tunneling. This is what we are doing actually. We are transferring those mathematical problems into the quantum simulation, so we find the minimum, global minimum much faster because of the quantum tunneling. But in a classical situation, you have to do one by one. That is not possible to do faster than. That is the promise that we are very excited about. Sorry for the long answer.
Yeah, I just wanted to add, like, all of this was figured out in the 48 hours, which was the hackathon time. So that was a very little, 2 sleepless nights is the result of our work. Yeah, and like we were able to solve for a very small subsection of the graph. And to answer the first question as well, we don't need to solve the entire graph in one go. We can divide and conquer it, which is a very normal classical approach as well. So what we were exploring was a hybrid solution where we actually use technologies which are their state-of-the-art classical technologies, as well as possibly machine learning. We came up with some really cool ideas of like being able to mimic quantum systems using ML as well in certain cases when we don't have that much time to run the quantum systems. So what we're trying to leverage is the current technologies available right now, as well as integrating quantum for the hard part. Yeah.
So to be clear, when I was talking about like 10 nodes, like takes an hour, that's IBM, right? D-Wave takes 3 minutes probably, or less than that, solving 35 nodes.
So with the strategy, like I know, I don't know how many intersections there are in the city, but I know there are around 1,300 managed intersections or controlled intersections. So would you like take 35 and divide it by 1,200, and then you do each one of those as a unit or a pod?
I think it would depend based on our capacity and how frequently we're communicating with the quantum computer or like using the algorithm as well, because it totally depends on how we structure the app. Because for one snowplow, they just need to see like the area around them. Like the next 35 nodes could be a lot, like the whole path for them for that day, right?
Sure.
So yeah, we'll just have to figure out how to decompose the graph in a strategic manner, like Jamal said, and then combine the solution together if we're limited, which we are going to be limited by the number of nodes that we can solve on one quantum computer or the technology we have access to then.
Yeah, I think we have to like add parameters one by one and see where does the QPU or hybrid solution breaks down, and then step back and try to by tailoring the problem in a way that we are finding. So the reason why quantum computer cannot find if you're defining your Hamiltonian in a way that there is a small gap because when you're doing it, so I don't want to go into the details, like into the weed here, but there is a clever way to chunk the problems so that it's possible to do it faster. So the point that I'm trying to across here is that it has to be some sort of feedback loop here. So when you're solving for that many nodes, then you have to see what is the result and then try to reiterate that, get the feedback, and then define your Hamiltonian again so you can do it in a way that is beneficial for classical and quantum part as well, if that makes sense.
Sure.
Sounds like you're pursuing this further. What's the next step? Like, are you incorporated? Are you applying for Chi Ventures program? What's happening?
We're figuring it out because, like I said, 5 people, we just came together. 2 of us are not here because one is in the US, one is in Switzerland. Yeah. So we're still figuring out what's next for us. We're just very excited with what we have been doing till now and excited to share it with all of you. And then let's see, David, what's next for us?
Let's put the question
pay you
to
for that question, Megan.
Let's put the question to the audience. Do you think this is something worth pursuing?
Another question. So you, in my head, you only did one area, and that's to maximize the amount of time and resources that you had in such a limited time frame. Now, I'm thinking that each area that you target going forward may have different variables. So by doing that exercise, you can refine or incorporate those different variables in each area of the city and then combine afterwards so that you are having a much more accurate approach. Would that, my understanding, be correct?
Yeah, I think it'll be a step-by-step approach. We might be able to do 1 or 2 variables to start with and then keep on growing the complexity of the problem as well. The reason we need to sort of like start soon or like start thinking about a quantum solution is also because it's not going to happen tomorrow. It's like we said in the slides, it's probably 3 to 5 years still where you're going to have like a solution that the whole city is using and it's perfect and super reliable and there's no problems with it, right? But if we look back even to like the classical approach that we had, it's always a feedback sort of an approach. You try a small test for a small area, you learn, and then you grow. So let's say we try for a very small area in downtown Calgary next winter, we will learn from it, be able to add more variables. Maybe traffic was not a big priority. I'm just saying, like, maybe something else was a bigger priority than what we expected. So it's gonna have to be a very agile sort of approach. And the great part is that while we're figuring out, like I think was previously mentioned as well, how we translate this problem into being quantum and quantum relevant, while we're figuring this out, the machines are gonna keep getting better. So because the algorithm can translate to a new machine. So as we keep figuring the problem out more and how we want to solve it, by the time we get to a good solution theoretically, the machines would also sort of get there. And that's the reason we need to start working on these sort of problems like as soon as we can.
So the main point here is right now, like hybrid solution is not something that hinders us to get the best result, because compared to the classical approach, we saw that it is comparable and sometimes much better because of the definition of the Hamiltonian. Not going into the details, but here's the thing. We don't want to fall behind. So if we start right now in city of Calgary, we have better chance to be ahead of other cities or municipalities or other countries. That's the thing.
I think one of the other benefits is you could take this solution. Every city has a snowplow issue. So ultimately, you can take this solution and export it to other cities around the world, right?
Indeed.
Yeah.
So as far as we can transfer the problem into Kubo optimization, we can use this approach. Probably Kubo can tell us more about this because they have the name, right?
Yeah, is that what Kubo stands for? I know the answer. That's why I'm asking him. Yeah. Any other questions? No? Okay, well, thank you very much. Fantastic.
Thank
Five.
you.
So thanks everyone for coming. Thanks for all the speakers and presenters for coming. And I think tomorrow's session is a private session. Is that right, Monique? Yeah, so we'll be shut down. But yeah, I hope you enjoyed the Wave, our grand opening, our launch. It's super exciting for us. We learned a lot, and the amount of engagement we had was incredible. So both in person and online. It's been a long 9 days. We had a 10-day launch. We're almost done. We're in our last mile, but it's been fantastic. Super exciting. Thanks to the entire Wave team. They all worked many, many hours to get this together and to get it done. And thanks to our fearless leader, Monique Nesset, for being our leader and getting us through this. And of course, Jason Cameron, but I don't think he's here. I think he went to pick up his daughter, but he's been working constantly. Every weekend he's been here trying to put the furniture together and all that, all the inside. And yeah, it's just been tremendous. So thank you very much, everyone.